Hello there and welcome to Physics with William, where large ideas are given a quieter room to breathe, and where physics is allowed to be thoughtful, curious, and just a little more human than it sometimes sounds in a textbook. Tonight, we're settling in beside a question that begins with something familiar and ends somewhere very close to the edge of what modern physics can comfortably describe. It is a question about electric force, which is one of those things that seems almost too ordinary to be mysterious. You rub a balloon on a jumper and it clings to the wall. You touch a metal handle after walking across a carpet and receive a tiny snap from the universe. Your phone lights up, your nerves carry signals, atoms hold their structure, lightning crosses the sky, and all the while this invisible interaction is at work, tugging and pushing, binding and repelling, shaping matter with remarkable confidence. But then comes the deeper question, the one we are really here for. How strong can electric force get before nature itself starts objecting? And that leads us towards something called the Planck charge, which sounds a little like a device you might plug into an impossibly advanced kettle, but is in fact a way of asking where the familiar rules of electricity may begin to meet their limit. Before we wander too far into that territory, I would love to know where you're listening from tonight, and what time it is in your little corner of the world. Perhaps it is late and the room is dim. Perhaps you're winding down after a long day, or perhaps you're simply the sort of person who enjoys letting a difficult question keep you company for a while. Either way, I am very glad you're here, and if you find this soothing, interesting, or just a pleasant way to let the mind drift while still having something to hold on to, then a like and a subscription would be warmly appreciated. It helps this quiet corner of science find the people who may need it, especially those who like their mysteries delivered at a slightly gentler pace. Now, electric force is a strange thing to live with, because we are surrounded by its consequences while rarely feeling that we understand it in any complete way. Gravity feels intuitive, things fall, things weigh something. A dropped spoon behaves exactly as your instincts expect. Electric force is not like that. It is at once more delicate and more powerful, more intimate and more dramatic. It operates on scales too small to see directly, yet its effects can be so strong that they determine the very architecture of the world. The reason your chair does not collapse into the floor is not because gravity suddenly becomes polite at close range. It is because the electric interactions inside matter are putting up an enormous resistance. The reason chemistry exists at all is because charged particles behave in very particular ways. The reason your own body is structured rather than smeared into an unhelpful cloud is that electric force is doing a tremendous amount of quiet administrative work every moment of your life. And yet most of the time we do not think of it as force in the same way we think of a shove or a pull. We think of electricity as current in wires, power points in walls, static in winter, maybe the faint warning sign on a laboratory cabinet, or the dramatic fork of lightning across a storm. We give it names depending on context, but the underlying idea is one of attraction and repulsion between charged things. Some charges pull toward one another, others drive one another apart. Already there is something interesting in that, because the universe seems to have built into it a rule that matter does not simply sit there passively. It responds, it notices, it rearranges itself based on these invisible instructions. Charge is not an ornament that particles happen to wear. It is one of the traits by which the world decides what can happen next. That alone would be enough to make electric force worth talking about, but it becomes even more interesting when you compare it with gravity. Gravity in human life feels like the dominant force. It keeps our feet down, the oceans in place, the moon in orbit, and our posture only moderately successful by the end of a long afternoon. It rules the large-scale universe with immense authority. Stars form under gravity. Galaxies rotate under gravity. Black holes are gravity in one of its more theatrical moods. But if you take two tiny charged particles and ask how strongly they interact electrically, compared with how strongly they attract one another gravitationally, the answer is not a small difference. It is not even a large difference in the ordinary sense. It is an enormous mismatch. Electric force on the scale of particles is astonishingly stronger. Gravity only appears dominant in our everyday lives because matter usually comes with electric charges that cancel out overall. Positive and negative balance each other so neatly that large objects are often electrically quiet. Gravity has no such cancellation in ordinary matter. It only attracts, and so it builds up across large masses like a patient bureaucrat who always gets the final word. This means electric force lives a double life. On one hand, it is hidden inside the ordinary balance of matter. On the other, when allowed to show itself without being neatly cancelled, it can become overwhelming. That is part of what makes the central question so compelling. If electric force is already so strong in the domains where we understand it, what would it mean to ask for its upper limit? Can there be such a thing as too much charge? Can electric interaction become so intense that the language we normally use begins to fail? And if it can, where does that happen? Not in the wall socket, certainly, not in a storm cloud, dramatic though that may be. Not even in the most powerful machine humanity has built. The scale we're heading toward is far stranger than that. It lies in a region where the known constants of physics begin to combine in ways that suggest a boundary, a place where familiar theories may no longer be enough by themselves. The name Planck charge points us toward that boundary. Max Planck, whose name appears attached to several of physics' most intimidating thresholds, helped establish a way of talking about nature using units built not from human convenience, but from the structure of physical law itself. Instead of measuring with reference to a meter stick or a ticking clock designed on Earth, Planck units try to describe scales that seem baked into the universe from the beginning. There is a Planck length, a Planck time, a Planck mass, and among these conceptual boundary markers sits the Planck charge. It is not a household quantity, and it is certainly not something you would ever meet directly in ordinary experience. It is more like a signpost. It tells us that when charge reaches a certain natural scale, something important is being approached. Not necessarily a brick wall. Physics is rarely kind enough to provide those. More often it provides a fog bank and then quietly waits for us to walk into it. What makes this especially interesting is that the question is not merely how much charge can be piled onto something, as though we were stacking invisible marbles into a cosmic bucket. The deeper issue is what happens when the force associated with charge becomes so intense that it can no longer be treated using the comfortable assumptions of classical thinking. At mild scales, we picture electric interaction in a fairly straightforward way. Objects have charge, they create fields, they push and pull, all very respectable. But nature is under no obligation to remain respectable when we crank the dial far enough. At sufficiently extreme scales, the vacuum itself, which we often imagine as empty, begins to behave less like nothing and more like a restless medium. Quantum effects step forward. Space ceases to feel like a passive stage. Energy and geometry begin to talk to one another more loudly. And somewhere in that crowded conversation, the meaning of maximum strength becomes harder to define. This is one of the things I enjoy most about physics. You begin with a question that sounds almost childishly direct. How strong can electric force get? It has the quality of a question one might ask while fiddling with magnets on a kitchen table, or receiving a static shock from a wool blanket. But then, if you follow it honestly, it carries you outward into deep theory. It makes you confront how we define strength in the first place. Is it force between particles? Is it field intensity? Is it energy density? Is it the point at which space, matter and quantum behaviour can no longer be discussed separately? Often in science, the hard part is not getting an answer. The hard part is discovering which question is actually hiding inside the one you started with. There's also something quietly satisfying about charge as a subject, because it is so fundamental and yet so easy to underestimate. A tiny imbalance of charge can produce a noticeable effect. A little static spark is not especially dangerous, but it is enough to make you pull your hand back and glare suspiciously at a doorknob as if it has developed personal feelings. Lightning, by contrast, is what happens when nature allows a truly massive electric imbalance to resolve itself in a way that is impossible to ignore. And even lightning, impressive though it is not close to the deepest scales physics can imagine. It is a weather event, not a cosmic limit. It is the sky clearing its throat, not the universe revealing its final volume setting. If electric force were a person at a dinner table, it would be the one who looks calm until the conversation turns serious, at which point everyone remembers who's been holding the room together the entire time. It governs the behavior of electrons around nuclei. It helps determine the rigidity of solids, the conductivity of metals, the transparency of glass, the chemistry of water, the signaling of neurons, the burning of stars in an indirect sense through the matter they are made of, and the whole daily business of matter refusing to simply pass through other matter. There is a reason so much of ordinary reality feels solid, structured, and dependable. Electric interaction, operating mostly behind the scenes, is an enormous part of that reason. And yet, there is a tension built into all of this. Whenever physics reveals a force that seems overwhelmingly strong in one domain, we become tempted to ask whether it can simply be extrapolated upward forever. Can we keep increasing it without limit? Can we imagine more and more concentrated charge, more and more violent repulsion, more and more compressed electric fields, all the way to infinity if we are patient enough? Experience suggests that nature usually dislikes naive infinities. They tend to be the points where our descriptions stop working rather than the places where reality itself loses composure. So when we ask how strong electric force can get, we're also asking where our theories start to overlap, interfere, and demand a deeper unification. This is where the topic becomes especially rich, because it brings together several very different moods of physics. There is the tidy classical mood, where electric force can be described clearly and elegantly. There is the quantum mood, where the vacuum is not empty, and charged interactions are mediated in ways that resist ordinary intuition. There is the relativistic mood, where energy, mass, and field strength must all be handled with more care. And somewhere beyond those familiar provinces there is the gravitational frontier, where Planck's scale ideas begin to matter, and where the separation between forces may no longer look the way it does to us now. The Planck charge belongs to that threshold region. It does not arrive as a complete explanation. It arrives as a warning label and an invitation. A quiet but important part of this story is that physicists do not introduce Planck quantities because they are fashionable, or because attaching Max Planck to something makes it sound respectable in a lecture hall. They do it because there seem to be certain scales where our most successful theories begin to point toward one another in a way that feels less accidental than usual. You can think of it a bit like reaching a coastline where two maps stop agreeing. One has served you well inland, another works beautifully at sea, but near the shore the overlap becomes messy, and that messiness is not a nuisance. It is information. It tells you that the region matters. The Planck charge is part of that coastal territory. It hints that extreme charge is not merely a stronger version of ordinary electric behavior. It may be a doorway into questions about the structure of reality itself. That is perhaps why this topic appeals to me. It starts with a force that seems familiar and ends by asking where familiarity breaks down. It lets us begin with the tangible and move slowly toward the abstract without ever losing the thread. You do not need to picture esoteric mathematics from the start. It is enough to notice that electric force is already extraordinary long before it becomes exotic. It holds atoms together in the sense that it shapes their internal life. It keeps everyday objects from collapsing into each other. It drives chemistry and technology and biological function. Then, once that is settled in the mind a little, we can start raising the stakes. What if we push charge harder? What if we imagine concentrating electric effect more and more? What starts to bend? What resists? What new behaviour emerges? There is also a more philosophical flavour here, though I will try not to become too grand about it, because physics is often most interesting when it stays close to the ground. Still, charge invites a certain kind of reflection. It reminds us that the world is not made only of visible objects moving through empty space, like billiard balls under good lighting. Reality is more relational than that. Things have properties that determine how they answer one another. Matter is not inert. It is responsive, structured by permitted interactions, constrained by invisible rules that turn a possible universe into this one. Ask how strong electric force can get, and you're not only asking about power, you're asking how far the universe allows one kind of relation to dominate before something more fundamental intervenes. For now, though, it is enough simply to arrive at the threshold of the question and sit with it for a while. The ordinary world gives almost no hint of how deep this goes. A spark from a blanket, a balloon clinging to a wall, the mild annoyance of hair developing opinions in dry weather, none of these look like entrances to the edge of physical law. They look like small domestic inconveniences. But physics has a habit of hiding its largest ideas inside the smallest events. The familiar often turns out to be the doorway. What seems like a simple push or pull between charges becomes, under closer inspection, a story about strength, scale, matter, vacuum, and the possible limits of description itself. So that is where we are heading, not in a rush and not all at once. We're going to take this carefully, beginning with the electric force as it first shows itself in the world we already know, and then gradually asking what it would mean to keep increasing that force, conceptually at first and then more seriously, until the comfortable picture begins to strain. Because before we can make sense of something as severe and natural sounding as the Planck charge, it helps to spend a little time with the quieter truth that electric force is already doing astonishing work all around you, in the lamp beside the bed, in the nerves behind your eyes, in the atoms of the air, and in the simple fact that the material world has shape at all. If you sit with that ordinary fact for a moment, it begins to feel less ordinary. The material world does not simply exist in a passive state, waiting for us to notice it. It is being held in its present form by relationships. Things answer to one another. Particles respond. Matter arranges itself according to rules that are invisible but never absent. And among those rules, electric force is one of the busiest and least theatrical. Gravity gets the grand scenery. It has planets, black holes, falling apples, and a long tradition of making physicists look wise while standing near cliffs. Electric force, by contrast, tends to work indoors. It is there in the glass, the wires, the molecules in your tea, the quiet discipline of atoms staying arranged as atoms, rather than wandering off like a meeting that lost its agenda. It rarely asks for applause, but it shapes far more of the immediate world than it is usually given credit for. When we say invisible pull, we should be careful, because electric force is not only a pull, it is also a push, and often a very decisive one. That duality is part of what makes it so important. Gravity in ordinary life only attracts, it gathers, it draws things inward. Electric force does something subtler and more versatile. Depending on the charges involved, it can bring particles together or drive them apart. It has a richer social life than gravity. Some charges get on well. Others would rather be on opposite sides of the room, or opposite sides of the galaxy if given the chance. Because of this, electric force can build structures and also prevent collapse. It can hold patterns in place and stop matter from casually merging into a single unhelpful lump. The world as we know it depends on both tendencies. Attraction alone would not do. Repulsion alone would not do. What matters is the careful balance. You can see the first hints of this in the smallest stable objects around us, the atoms. Every atom is built around a positively charged nucleus, with negatively charged electrons associated with it. Already this tells you something remarkable. Matter is not built from tiny pieces that merely sit next to one another. It is built from charged components whose behavior depends on attraction. Without that attraction, the electron would not remain associated with the nucleus in any meaningful sense, and chemistry would not exist. No molecules, no solids, no liquids, no air, no biology, no quietly overcomplicated human beings wondering about the limits of electric force before bed. The simplest fact of atomic existence already rests on electric interaction. But that attraction cannot be the whole story, because if everything with opposite charge simply collapsed into everything else with no restraint, atoms would not have structure either. They would not have size. They would not have distinct energy arrangements. The universe would be far less interesting and also far more difficult to furnish. So electric force is always operating in a context, never in isolation from the other principles that govern matter. It attracts electrons toward nuclei, yes, but quantum rules determine how that attraction can express itself. The result is not collapse but structure, not chaos but pattern, not a featureless concentration of charge, but shells, arrangements, bonding behavior, reactivity, stability, and all the rest of the chemical world. The electric force provides much of the motive power, but nature adds constraints so that the outcome is a world rather than a catastrophe. Once you move beyond individual atoms and begin considering how they gather into matter, electric force becomes even harder to ignore. Take something as simple as a table. It looks solid. It feels solid. It carries your books, your cup, and perhaps the accumulated evidence that you meant to tidy up yesterday. But solidity is not some separate ingredient sprinkled onto matter by a benevolent supplier. It emerges from interactions between atoms and electrons. The reason your hand does not pass through the tabletop is not that the atoms in your hand and the atoms in the wood are tiny billiard balls colliding in a purely mechanical sense. It is that the charge structures of those atoms resist being pushed into the same states and spaces. Electric interactions, together with quantum principles, create the ordinary firmness of matter. The table feels solid because electric force is taking its responsibilities very seriously. That fact alone can change the way you look at the room around you. The chair is not solid because it is full of some special substance called solidity. The walls are not firm because firmness is their default mood. They are made of atoms. Those atoms are structured by charge, and the charged components of matter behave according to strict rules that create resistance, shape, and stability. What seems inert is actually dynamic. A quiet object is not an inactive one. It is a successful arrangement of electric relationships. This is also true of liquids, though in a slightly different way. Water, for example, is one of the strangest ordinary substances in the universe, and much of its behavior comes down to electric structure. A water molecule is not electrically neutral in the sense of being featureless. Its charge is distributed unevenly. One end behaves a little differently from the other. This allows water molecules to interact with one another in ways that give rise to cohesion, surface tension, and the many peculiar properties that make water so useful for life and so annoyingly determined to cling to every surface, except the one you wanted it to remain on. A spilled glass of water is a small domestic event, but it is also a display of electric interactions at work. The droplet beads, spreads, sticks, and slides according to the invisible pull and push between molecules. Then there is chemistry more broadly, which is in many ways the long story of electric force negotiating with itself. Why does oxygen react so eagerly with some things and not with others? Why does sodium become dramatically sociable in the wrong circumstances? Why can carbon build so many structures, from diamond to graphite to the compounds that make life possible? In each case, the answer is rooted in how electrons are arranged and how atoms can lower or raise their energy through new electric configurations. Chemistry is not a separate kingdom detached from physics. It is what electric interaction looks like when it becomes elaborate enough to write long, very expensive textbooks. Even your own body is a running conversation in charge. Nerves transmit signals through changes in electrical conditions across membranes. Muscles contract because charged ions move in controlled ways. The heart keeps rhythm through coordinated electrical behaviour. The brain, that soft and slightly overworked organ with which you are listening to these words, depends on electric processes for every thought, memory, mood, and attempt to remember why you entered the kitchen. This does not mean you are merely electricity in some dismissive sense. It means that electric force is one of the essential languages through which living matter maintains itself. Life is not separate from the physical world. It is one of the most intricate things the physical world does with its available forces. There is something almost humbling about that. Electric force is not just responsible for laboratory demonstrations and weather phenomena. It is involved in perception, movement, sensation, metabolism, and memory. Every time a neuron fires, the body is making use of principles that also govern lightning, static, atomic structure, and the stability of solids. Nature is economical that way. It reuses its best ideas. And yet for all this intimacy, electric force remains hidden from direct sight. We do not see charge itself. We see what it does. We see the bulb glow, the hair lift, the spark jump, the chemistry proceed, the screen respond to a fingertip, the muscle move, the storm gather charge until it finally decides subtlety has been overrated. In that sense, electric force is a little like wind. You do not see the thing itself, only its influence on whatever is willing or unfortunate enough to be moved by it. A charged object does not announce its state with a tiny sign. It announces it by changing the behaviour of other things nearby. This is why the simplest experiments with charge still feel a bit magical. Rub a balloon on fabric and it begins sticking to surfaces. Run a comb through dry hair and loose strands rise as if reconsidering their long-term commitments. None of this feels intuitive in the same way a falling stone feels intuitive. It feels more like a private agreement between materials that we are allowed to witness but not entirely understand. The reason, of course, is that electric charge can be transferred or redistributed, creating imbalances that lead to attraction and repulsion, but explanation does not completely rob it of charm. If anything, it adds to it. There is something delightful about the fact that a mundane object like a balloon can briefly become a visible ambassador for one of the deepest interactions in nature. The same force scales upward into far more dramatic settings. Lightning is perhaps the most obvious example. A storm cloud becomes a place where charge is separated and accumulated until the electric conditions between cloud and ground, or within the cloud itself, become extreme enough that the insulating air can no longer maintain its composure. What follows is a rapid discharge, brilliant and violent, a moment in which the atmosphere briefly behaves less like empty space and more like a conductor under protest. It is one of the few times electric force becomes impossible to romanticize into harmlessness. A static spark from a blanket is mildly irritating. Lightning is the same basic interaction playing at a scale large enough to remind you that nature has access to settings far above your preferred comfort level. Still, even lightning is only a local expression of something much more general. Electric force shapes stars indirectly by determining the behaviour of the matter they are made from. It governs plasma, that state of matter in which electrons and nuclei are no longer politely bound together, but move in a charged crowd. Most of the visible, ordinary matter in the universe is thought to exist in plasma form, especially in stars and interstellar environments. So while we tend to think of electric effects as something that belongs to sockets, batteries, and mildly alarming winter doorknobs, the universe has been using charge on a grand scale long before it invented us and our tendency to name things after whoever was standing nearest the chalkboard. What makes electric force especially fascinating is that its apparent strength depends so much on circumstance. In one context, charges cancel neatly, and matter seems calm. In another, slight imbalances lead to obvious effects. In yet another, huge concentrations produce spectacular discharges or intense atomic behaviour. This gives the force a kind of layered personality. It is not absent when quiet, only balanced. The world around you is electrically busy even when it appears uneventful. Every neutral object is neutral because positive and negative charges are present in just the right proportions, not because charge has left the building. That point matters, because it explains why the everyday world is not constantly exploding into electric chaos. Imagine if every object around you carried even a modest net charge without cancellation. Chairs would object to flaws, cutlery would develop strong opinions about plates, and getting dressed in the morning would become a highly strategic exercise in electrostatic diplomacy. The reason daily life is manageable is that matter tends toward overall neutrality. Positive and negative charges pair up so effectively that their larger scale effects mostly cancel. Electric force remains crucial internally while becoming less obvious externally. It is a hidden architecture, and hidden architecture is often the most important kind. We rarely think about the beams inside a wall until something goes wrong, but they determine the whole shape of the house. Electric force plays a similar role in reality. It is embedded so deeply in the structure of matter that we overlook it precisely because it is working well. The better it does its job, the less often we stop to notice it. The world feels normal, stable, dependable. Cups stay cups. Nerves signal, molecules form, solids resist compression. We become accustomed to these things and forget that behind them lies a precise and powerful interaction that could, under slightly different circumstances, make the same world far less hospitable. There is also a lovely tension in how electric force combines intimacy with range. At the atomic level, it is decisive, shaping the microstructure of matter, yet electric fields can extend across space, influencing other charges without direct contact. This offended some early intuitions in physics, because human beings are understandably suspicious of anything that appears to act at distance. We like our causes local and visible. A hand pushes a door, a foot kicks a ball. But electric force does not wait for physical touching in the ordinary sense. A charged object modifies the conditions around it, and another charged object responds. That is one reason fields became such an important concept in physics. They gave a way of understanding interaction not as magic or remote telepathy, but as something structured through space itself. Even so, there is still something eerie about it in the best sense. Charges answer one another across emptiness. Matter carries within it the ability to influence distant matter. Space is not merely emptiness separating objects, it is the medium in which these influences are defined and transmitted. Once you begin thinking that way, the world feels a little less like a collection of isolated things and a little more like a network of possible interactions. Perhaps that is why electric force lends itself so well to metaphor, though one must be careful not to get carried away. It is tempting to speak of attraction and repulsion in almost social terms, as though particles had preferences, loyalties, grievances, and very strong boundary issues. That language can be charming in moderation, but the real point is more exact. Charge is one of the properties by which particles participate in the structure of the world. It is not decoration, it is instruction. It tells the universe how a given particle may respond, and in aggregate those responses become chemistry, matter, technology, life, and weather. Notice too how quickly scale changes our emotional response. The same basic interaction can feel playful in static cling, useful in electronics, essential in biology, beautiful in auroras, and terrifying in lightning. That alone should make us cautious about treating electric force as a single simple thing. Its character depends on context. A mild electric signal can coordinate the beating of a heart. A stronger uncontrolled one can stop it. A carefully regulated current can preserve information in a computer. An uncontrolled discharge can ruin the device and possibly your afternoon. Nature does not care whether we label something convenient or catastrophic. It only cares about conditions, and conditions are exactly what we all need to think about as this story moves forward. Because asking how strong electric force can get is not like asking how tall a mountain is, where you can at least imagine walking toward the thing with a notebook and an optimistic hat. It is more like asking, under what conditions the very meaning of electric strength begins to change. Before we can go there, though, it helps to appreciate the force in its ordinary abundance. It shapes the world not only in dramatic events, but in the quiet persistence of form. The arrangement of atoms in a crystal, the flexibility of a metal wire, the transparency of air, the behavior of salt in water, the texture of paper, the conductivity of your skin, the operation of the eye, the taste of food, the structure of DNA, the stability of proteins, the carrying of signals through nerves. All of this depends in one way or another on charged particles interacting according to rules that are both strict and astonishingly productive. So much of human life is lived inside electric consequences. Our houses, tools, screens, engines, sensors, medical devices, instruments, communications and kitchens all depend on our ability to work with charge in controlled ways. That control is one of civilization's quiet triumphs. We have learned to persuade charged particles to move in orderly patterns through circuits, to store energy, to switch states, to process signals, to illuminate rooms, to preserve food, to scan brains, to send voices across oceans, and to let someone lie awake at night watching a video about the deep structure of reality. There is something very human in taking an invisible force that once announced itself mostly through storms and static, and turning it into a partner in nearly every aspect of modern life. Yet for all that familiarity, the force itself remains deeper than our conveniences. We have learned to use it long before fully exhausting its meaning. That is usually the way with physics. Application arrives early. Understanding takes its time. People were making use of electricity before anyone had a complete theory of the atom, and even now the deeper questions remain alive. Why this charge? Why these strengths? Why this balance between the forces of nature? Why should matter be built from particles carrying precisely the properties that let the world become complex without disintegrating? These are not questions a light switch can answer, however efficiently it performs its duties. So when we call electric force the invisible pull that shapes the world, we are really saying something more precise. It is the invisible interaction that gives matter its patterns, its resistance, its chemistry, its biological activity, and much of its technological usefulness. It is one of the reasons the universe is not bland. It allows form to exist, change to occur, and complexity to grow. It is hidden not because it is weak, but because it is woven so thoroughly into the fabric of the ordinary that we stop seeing it as exceptional. The next step is to make that hidden architecture a little more explicit. Up to now, we have spoken in broad terms about attraction, repulsion, balance, and structure. But physics, once it has admired a thing for a while, eventually wants to measure it. How exactly does this force depend on distance? How does one charge influence another? What determines whether the effect is slight or overwhelming? The world has been giving us hints all along, from rubbed balloons to atoms to lightning, and gradually those hints were turned into one of the cleanest and most revealing laws in classical physics. And once that law is in view, the question of how strong electric force can become starts to sharpen into something we can follow much farther. Once physicists began trying to describe electric force with real precision, the conversation had to change. It was no longer enough to say that charged things sometimes attract and sometimes repel, though that remains perfectly true and still quite useful if you're dealing with a balloon, a wool jumper, or a hairstyle that has taken a strange turn in dry weather. What was needed was a language that could tell us not only what happens, but by how much. How much stronger does the interaction become if the charges are larger? How much weaker does it become if the particles are farther apart? How exactly does the force depend on distance, and how should we think about its direction? At that point, the invisible pull and push of the world had to become something measurable. It had to be given grammar. That grammar is what we now call Coulomb's law, named after Charles-Augustin de Coulomb, the French physicist who helped turn electric interaction from a collection of striking observations into something quantitatively clear. The law itself is one of those rare achievements in physics that feels both simple and profound. It takes a behaviour that seems slippery and untouchable and expresses it in a way that lets the mind begin to work with it confidently. Once you understand the basic idea, you can see why electric force is enormous at small scales, why it fades with distance, why neutrality matters so much in ordinary objects, and why even a modest amount of unbalanced charge can become surprisingly important. The central thought is this: the electric force between two charged things depends on two main ingredients. First, it depends on how much charge each one has. Larger charges interact more strongly. Second, it depends on how far apart they are. The farther apart they are, the weaker the force becomes. That much might sound almost obvious, but nature is not always obliged to honour obviousness. What makes Coulomb's law especially elegant is the precise way the weakening happens. The force does not merely decline a bit as distance increases, it falls off very quickly, according to the same general pattern that also appears in gravity and in the spreading of light from a source. This pattern matters because it reflects something about geometry. Imagine that an influence radiates outward from a point into space. As it spreads, it is distributed over larger and larger imaginary spheres surrounding the source. The surface of those spheres grows rapidly with radius, so the intensity at any given point gets diluted as the influence spreads outward. In a sense, space itself is doing bookkeeping. The farther away you go, the more room the influence has had to spread, and so the weaker it becomes at any particular location. Electric force follows that rule. It is strongest when charges are close, and it drops off sharply as they separate. That one fact immediately explains why electric interactions are so dominant inside atoms and molecules, where particles are separated by truly tiny distances, while large ordinary objects can sit in a room together without erupting into electrostatic drama. At very small scales, closeness magnifies everything. A nucleus and an electron are not just related by charge in an abstract sense. They are close enough for the electric interaction to matter enormously. By contrast, if two neutral chairs stand a few feet apart, the net electric effects between them are tiny because their internal charges are balanced and their distance is comparatively large. Distance is not the whole story, but it is a major part of why electric force can be both intimate and explosive in one setting, yet almost invisible in another. The law also gives us direction, and this is where the language becomes especially useful. Electric force is not simply a quantity with size, it points somewhere. If two charges are of the same kind, the force drives them apart. If they are of opposite kind, it pulls them together. The line of action runs along the line joining the two charges. That means the electric interaction is not vague or diffuse in the way we sometimes speak about influence in daily life. It is specific, it has magnitude and direction. Physics cares deeply about both, because a force that points east is not the same as an equally strong force that points north, and a force that attracts is not the same as one that repels. Once electric force is written in this way, as something directional and measurable, it can be treated with the same seriousness as any other force in mechanics. This may sound routine to us now, but historically it was a major shift. For a long time, electricity had the reputation of being one of nature's more temperamental subjects. It produced sparks, shocks, strange attractions, and theatrical demonstrations in salons and laboratories, but it did not yet seem as disciplined as falling bodies or planetary motion. The challenge was to show that electric behaviour could be studied with the same exactness as more familiar mechanical phenomena. Coulomb did this by using a torsion balance, a delicate device that could detect very small forces by measuring how much a suspended object twisted under the influence of another charged object nearby. There is something charming about that image. Invisible force, measured by the quiet turning of a fine instrument. No thunder, no lightning, just careful patience and a willingness to trust that nature will answer if asked politely enough. What emerged from that work was not merely a rule for experimenters, it was a new way of thinking, Once you know that electric force can be quantified in a clear and reliable way, you can begin building theory around it. You can predict how charges will move. You can calculate how systems of multiple charges behave. You can understand why conductors and insulators matter. You can develop the concept of the electric field, which is one of the most powerful ideas in all of physics. The law becomes not just a result, but a doorway. The notion of the field deserves a slow look because it changes how we imagine electric interaction. Instead of thinking that one charge somehow reaches across empty space and grabs another by an invisible thread, physicists began to describe each charge as creating a condition in the space around it. That condition is the electric field. Another charge placed in that field experiences a force. This is a more structured and satisfying picture than simple action at a distance. It says that space near a charge is not just empty background. It is altered in a way that affects what other charges will feel if they enter that region. A charge creates an environment. Another charge responds to that environment. Once you think in terms of fields, Coulomb's law becomes a statement not only about pairwise force, but about the shape and intensity of the electric landscape around charged objects. A single, isolated charge produces a field that spreads outward in all directions. If the charge is positive, the field points outward. If the charge is negative, the field points inward. These arrows are not little physical rods poking through space. They are a map of how a positive test charge would be pushed or pulled if placed there. Already you can see why language matters so much. Without clear conceptual tools, electricity remains a collection of curiosities. With them, it becomes a geometry of influence, and influence can be added. This is another quiet triumph of electric theory. If you have several charges present, each one contributes to the field, and the total effect can be found by combining those contributions. That simple idea turns out to be extraordinarily powerful. It means complex electric situations can be built up from simpler ones. The world does not have to be reinvented from scratch each time. A pair of charges gives one pattern. Add a third, and the pattern becomes richer. Arrange many charges and you begin to model molecules, materials, conductors, capacitors, and eventually entire technologies. Much of physics advances by finding ways to combine simple truths into complicated realities, and electric force is a classic example of that. There is also a very helpful contrast here with gravity. Superficially, the two laws look somewhat alike. Both forces depend on a property of the interacting objects, and both become weaker with distance according to the same broad geometric rule. But the emotional life of the two forces could not be more different. Gravity only attracts. Electric force attracts and repels. That one difference makes the world vastly more complicated and more interesting. Gravity gathers matter on the larger scales because it has no balancing opposite in ordinary mass. Electric force, by contrast, constantly negotiates between opposites. It allows cancellation, balance, screening, structure, tension, and separation. It can build compact arrangements and also tear them apart. It can stabilize and destabilize. In that sense, Coulomb's law is not just a measure of strength, it is a statement of possibility. Think about what cancellation means for the world around you. A neutral object is not electrically inactive because it lacks charged components. It is neutral because positive and negative contributions balance. This would be impossible if electric force behaved only one way. The existence of two kinds of charge allows matter to settle into patterns of near neutrality while still retaining enormous internal electric activity. That is why the world can be structurally rich without being electrostatically unlivable. Chairs do not launch themselves across the room because their total charge is close to balanced. Atoms hold together because internal opposites attract, while quantum rules and mutual repulsions prevent collapse. Molecules form because charges can arrange themselves into stable compromises. Coulomb's law gives the intensity. The existence of opposite charge types gives the universe its room for complexity. The law also teaches something important about scale. When people first hear that electric force is vastly stronger than gravity between elementary particles, it can sound almost unbelievable. After all, gravity feels important, and electricity often feels optional until the battery dies. But Coulomb's law makes the situation clearer. At very small distances, the electric interaction between charged particles is immense. The reason it does not dominate the motions of planets and apples in the same way is not because it lacks strength. It is because large objects are usually close to electrically neutral overall. The internal charges cancel at larger scales, leaving gravity, weak though it is, as the main uncancelled long-range effect in bulk matter. So the law does not merely tell us about force, it helps explain why different forces seem to rule different realms. There is something almost philosophical in that. What appears dominant depends on what survives cancellation. In the intimate life of matter, charge is king. In the architecture of stars and galaxies, gravity takes the throne because it accumulates without opposition. The world is not governed by whichever force is strongest in the abstract, but by whichever one remains relevant under the conditions at hand. Coulomb's law is one of the reasons we can say this with confidence, rather than as a poetic guess. Still, classical clarity can be deceptive if one is not careful. A law this elegant invites the temptation to think the subject is finished. If electric force depends on charge and distance in such a clean way, perhaps all that remains is bookkeeping. But nature enjoys letting simple laws govern only part of the story. Coulomb's law works beautifully in the classical regime for stationary point-like charges, and for many situations that can be approximated that way. Yet even within classical physics, real materials, extended objects, motion, and changing fields add layers of richness. Charges in motion generate magnetic effects. Time-varying electric and magnetic fields intertwine. Radiation appears. Eventually, Maxwell's equations gather these threads together into a much grander framework. Even so, Coulomb's law remains foundational, because it captures the quiet heart of electrostatics. It tells you how static charge behaves before the full drama of electromagnetism begins. It is like learning the grammar of a language before tackling poetry, legal documents, or family arguments conducted at high speed. Without that grammar, the later complexity would feel shapeless. With it, the rest begins to make sense. The historical aspect matters here too, because physics does not arrive fully formed. It earns its clarity. Coulomb and those around him were part of a period in which scientists were gradually learning how to domesticate the invisible, not tame it in the sense of making it mild, but tame it conceptually. Heat, electricity, magnetism, light, and eventually the atom all had to be brought from the realm of vivid experience into the realm of disciplined measurement. That shift is one of the most beautiful things about science. A phenomenon begins as mystery, becomes pattern, then law, then language, and then, with enough patience, part of a larger worldview. Coulomb's law is one of those turning points where an oddity of nature becomes a sentence in the universe's instruction manual. It also changes the meaning of a question like the one guiding this whole series. How strong can electric force get? Before you have a law, that question is impressionistic. After you have one, it becomes precise. Stronger in what sense? Between what charges? At what distance? In what medium? Under what conditions? Already the question sharpens. Already it becomes clear that force is not just some vague quantity that can be imagined getting louder like music from another room. It is relational. It depends on the interacting charges and their separation. Increase the charge and you increase the force. Decrease the distance and the force rises sharply. That alone tells you why atomic and subatomic realms are so intense. It also hints at why asking for a maximum may involve pushing both charge and scale toward extreme conditions. There is a lovely pedagogical effect in this as well. Coulomb's law teaches restraint. It prevents us from talking about electric force as though it were a kind of substance stored in an object. A charged object does not simply contain force the way a pantry contains soup. The force appears in interaction. It is about relation, not possession. A single charge creates a field, yes, but the force is defined through what happens when another charge is present. That relational mindset turns out to be good training for deeper physics, where so much depends on interaction rather than isolated essence. We should also say something about media, because the environment matters. Electric force between charges is not always the same in every material setting. In vacuum, it has one familiar strength. In matter, surrounding particles can respond, polarize, and partially screen the interaction. This is why electric behavior in a material is not just a trivial copy of its behavior in empty space. Glass, water, metal, air, biological tissue, and vacuum all host electric influence differently. The field rearranges other charges, and those rearrangements alter the effective interaction. Once again, the universe refuses to let a simple law remain simplistic for long. It gives clarity first, then complications, and ideally enough time to appreciate both. This matters enormously in technology and chemistry. In a conductor, charges are free enough to move that electric imbalances rearrange quickly. In an insulator, charges are more constrained, so the response is different. In polar materials, electric structure can align in ways that influence forces and fields. In water, ions and molecular polarity make electrostatic interactions especially rich. Life itself depends on these contextual subtleties. Proteins fold in charged environments. Cell membranes maintain electric differences. Signals propagate through ionic movement in watery structured media. Coulomb's law is still at the root, but real life adds layers upon layers of participation. And yet the clean core remains remarkably durable. Like Newton's mechanics in the everyday world, Coulomb's law gives a first picture so powerful that it becomes part of how physicists instinctively see. When two charges are mentioned, the mind immediately begins asking how large, how far, what sign, what field, what environment. That is what it means for a law to become language. It stops being a memorized statement and becomes a way of thinking. Once that happens, even simple scenes are recast. A charged rod brought near scraps of paper is no longer a parlour trick. It is a field influencing matter. A lightning cloud is a vast charge separation waiting for conditions to fail. A chemical bond is an arrangement of charged particles seeking a stable pattern under quantum rules. The world becomes more legible. Legibility, however, is not the same as finality. The closer we move toward the most extreme scales, the more this classical language begins to strain. A law that describes static point charges beautifully does not by itself tell us what happens when fields become so intense that the vacuum is no longer passive, or when quantum fluctuations matter, or when energy concentration pushes toward gravitational relevance. Those are later concerns, but you can already feel them gathering at the edges. The better we understand the clean classical story, the more sharply we notice where it may cease to be enough. For now, though, it is worth lingering with the quiet achievement itself. Coulomb's law gives us the first disciplined sentence in the language of electric force. It tells us that charge is measurable, that interaction is structured, that distance matters in a precise geometric way, and that attraction and repulsion are not moods but lawful responses. It lets us move from marvelling at electric behaviour to reasoning about it, and once reasoning begins, the door opens to deeper questions, because a law this clear naturally invites the next one. If electric force depends so powerfully on charge and distance, what happens when either becomes extreme? How intense can attraction or repulsion become before ordinary matter starts to protest? At what point does the calm language of electrostatics begin to run into the more severe vocabulary of quantum behaviour, instability, and breakdown? That is where the story starts tightening, because once the grammar is in place, it becomes possible to ask just how far the sentence can be pushed before nature corrects our tone. At first glance, attraction seems like the calmer side of electric force. Repulsion gets most of the dramatic roles. It is the spark that jumps, the static shock that makes you flinch, the visible refusal of like charges to stay politely together. Attraction, by contrast, often hides inside structure. It is the quieter tendency, the one that draws opposite charges together and allows matter to organize itself into atoms, molecules, solids, liquids, and living things. It feels constructive, helpful even. If repulsion is what makes charge noticeable, attraction is what makes the world possible. But that impression only holds if the attraction stays within the ordinary range of conditions that matter has evolved to handle. Push it harder, squeeze the participants closer, or ask it to act in more severe settings, and the polite face of electric attraction begins to change. The same force that allows atoms to exist can, under the wrong circumstances, become relentless. This is one of the most interesting features of physics. The qualities we attach to a force in ordinary life are not reliable guides to how that force behaves in extreme conditions. Water is refreshing until it arrives as a flood. Gravity feels familiar until it becomes a black hole. Electric attraction seems gentle while it is busy helping electrons remain associated with nuclei. But if you follow the logic further, it leads to a serious question. How close can opposite charges be pulled before something else pushes back? Because something always does. Nature is not in the business of allowing simple trends to continue forever without complication. There are always counterweights, thresholds, and competing principles waiting just off stage. The first place to see this clearly is in the atom itself. A negatively charged electron is attracted to the positively charged nucleus. That much we have already allowed into the room, but if electric attraction were the only consideration, the picture would be very strange indeed. A classical thinker might expect the electron to spiral inward and crash into the nucleus, the way a stone falls toward the ground. Opposites attract, after all. The closer they get, the stronger the force becomes. So why does the atom not simply collapse? Why does matter have size? Why does a hydrogen atom have a stable structure instead of ending as one tiny overcommitted point? The answer is that electric attraction is real, strong, and essential, but it does not act alone. Quantum rules intervene. The electron does not behave like a miniature planet circling a sun under ordinary mechanical rules. It occupies allowed states. It has a wave-like description. Its position and momentum cannot both be pinned down with unlimited precision. There is a built-in resistance to being confined too tightly. In a very deep sense, the atom exists because attraction is strong enough to bind, but not free to do whatever it likes. Structure comes from the tension between pull and restraint. If attraction were weaker, atoms would not hold together properly. If restraint were absent, they would collapse. Matter lives in the compromise. That compromise is one of the great balancing acts of the universe. The electron is drawn inward, but not all the way. The nucleus is compact and positive, but not an unlimited sink into which every negative charge can simply fall. Quantum mechanics does not remove electric attraction. It civilizes it. It tells the attraction how it may express itself. So when we ask what happens as attraction becomes extreme, we're already asking about a conflict between tendencies. The electric force says closer. Quantum structure says not arbitrarily closer. Stability is the treaty that results. This becomes more striking when you move from a simple atom to heavier elements. A nucleus with more positive charge exerts a stronger attraction on electrons. That is why electrons in heavy atoms can be held more tightly, especially those nearer the center. The inner electrons in such atoms are not living the gentle life of an outer chemical electron idly wondering whether to participate in a bond. They are deep in the electric well, strongly bound, moving in ways that begin to reflect relativistic effects. Already the familiar picture grows more intense. Attraction is no longer a quiet background condition. It becomes a serious player in determining how the atom behaves, how chemistry shifts across the periodic table, and how energy levels arrange themselves. That progression matters because it shows that stronger attraction is not just a conceptual possibility. Nature already explores it. As nuclei grow more positively charged, they pull harder on their electrons. The behavior of those electrons changes in measurable ways. Their effective speeds increase. Their orbitals contract or rearrange. The chemistry of heavy elements can differ partly because the innermost electrons are held with such severity that ordinary approximations begin to lose their innocence. Extreme attraction does not wait until the far edge of theory. It begins announcing itself in the heavier parts of the periodic table. Still, even that is only a prelude. The deeper question is what happens if one keeps turning the dial. Suppose the positive charge at the centre were increased further and further. Suppose an electron were exposed to an electric attraction so intense that the ordinary separation between bound state and collapse began to blur. Would the atom simply become more tightly bound forever? Or would the theory itself begin to signal distress? This is where physics starts to become wonderfully stern. It does not let you take a good idea and abuse it indefinitely. One way to understand the tension is to remember that binding an electron more tightly generally means confining it more strongly. But confining a quantum object very tightly changes its behaviour. The more localized it becomes, the more uncertain its momentum must be. That uncertainty is not a matter of sloppy measurement. It is built into the structure of quantum reality. So a stronger attraction tends to squeeze, while quantum rules ensure that squeezing comes with cost. At some point, the energy bookkeeping becomes serious. You cannot just compress a charged quantum particle into an ever smaller region and expect the rest of physics to remain politely unchanged. Then there is relativity, which joins the discussion once energies and effective particle behaviour become sufficiently extreme. In ordinary atoms, non-relativistic approximations can often get you surprisingly far. But for very strongly bound electrons, especially in heavy atoms, relativistic corrections matter. The electron is not merely sitting in a stronger electric field. It is responding in a regime where its behaviour must be described with a theory that respects the deeper relationship between energy, momentum, and the structure of space-time. And when that happens, the neat image of attraction simply getting stronger becomes tangled with more serious questions about the vacuum itself and the possible creation of particle pairs. That may sound like a sudden leap, but it is exactly the kind of leap extreme conditions force upon us. The vacuum in quantum field theory is not an inert void. It is the lowest state of a restless set of fields. If an electric attraction becomes strong enough, especially near an extremely highly charged nucleus, or an equivalent intense field configuration, the vacuum may no longer remain merely a passive background. It can be driven into action. In a sufficiently severe electric field, the energy landscape changes so much that electron and positron pairs can become relevant in a very direct way. What looked at first like a simple story about one electron being pulled inward becomes a story about the field itself drawing matter out of the vacuum. This is one of those moments where physics calmly reveals that the deeper truth is stranger than the first question. You ask what happens when attraction becomes extreme, expecting perhaps a more tightly bound electron, a more compact atom, maybe a more intense version of familiar behaviour. And nature replies that if you push hard enough, you do not merely change the atom. You challenge the stability of empty space as described by the theory. The vacuum has opinions. It does not just sit there taking notes. An especially interesting case arises in the study of super-heavy nuclei. These are nuclei with so much positive charge that physicists have long wondered what happens to the electrons around them if the nuclear charge exceeds certain critical values. The idea is not merely that electrons become more tightly bound. It is that the binding may become so extreme that the usual description of electronic states merges into something more radical. Under such conditions, the vacuum may spontaneously produce an electron that occupies the deeply bound state, while the corresponding positron escapes. In plainer terms, the attraction becomes so strong that it helps pull a real electron into being from the quantum vacuum, leaving its positively charged counterpart to fly off. Attraction ceases to be merely binding. It becomes generative in a disturbingly literal way. That is not an everyday event, and no one is mistaking the kitchen table for a supercritical field laboratory, but it tells us something crucial. Electric attraction is not infinitely well behaved. There are thresholds beyond which the language of a simple bound particle is no longer enough. The field can become so strong that the distinction between background and participant breaks down. This is exactly the kind of sign that tells physicists they're approaching a limit of ordinary description. It also helps explain why the question of maximum electric strength is not just about making charges larger and distances smaller in a childish way, as though we were stacking an impossible number of magnets into a drawer and waiting for drama. Extreme attraction forces the rest of the theory to respond. Quantum mechanics responds through confinement costs and allowed states. Relativity responds by changing the deeper energy relations. Quantum field theory responds by reminding us that the vacuum is full of potentiality and may become unstable under sufficiently strong conditions. Nothing in nature is ever merely turned up. It is turned into something else. There is another form of extreme attraction that shows up in dense astrophysical matter, though now the story becomes a little more crowded because the strong nuclear interaction and gravity join the conversation. In the cores of very dense stars, such as white dwarfs and neutron stars at different stages of compression and evolution, electric effects remain important in the structure of matter. Electrons can be forced into conditions where their energies become enormous. In some cases, matter is compressed so much that electrons are captured by protons, producing neutrons and neutrinos. This is not a simple consequence of electric attraction alone, but it is one more example of how the familiar balance of charged matter can be transformed under severe conditions. Push matter far enough and the ordinary architecture of atoms no longer survives. The world does not remain atomic out of stubbornness. It remains atomic only under conditions where the existing balances still make sense. That point is worth slowing down for. We sometimes speak of atoms as if they were the natural final form of matter, the little indivisible citizens of reality. They are not. They are stable arrangements under a particular range of conditions. Change those conditions enough, and even the atom gives way. Pressure, energy, density, field strength, all of these can drive matter into new organizational modes. Extreme attraction is one route by which ordinary structure becomes unstable. It reveals that the everyday world is not the only way matter can be. The same logic extends to chemistry. Chemical bonds are made possible by electric attraction, operating at a scale and in a manner moderated by quantum rules. But not all attraction produces pleasant or stable chemistry. In highly ionized plasmas, in intense radiation environments, or under very strong external fields, the ordinary balance of electrons among atoms can be badly disrupted. Electrons can be stripped away, redistributed, or driven into unusual states. Molecules that are stable on Earth may not survive in such settings. Attraction remains present, but the context has changed so much that its familiar role has changed with it. The force is the same in principle. The world it is acting in is not. This is one reason why extreme conditions are so educational. They expose the assumptions hidden inside normality. On Earth, in a room, at moderate temperature and pressure, atoms and molecules behave in ways that feel dependable. We begin to think that their behavior is simple. It is not simple, it is just stabilized by a fortunate range of conditions. Once those conditions are withdrawn, the deeper severity of the underlying interactions becomes visible. Attraction can strengthen. Bonds can distort. Electrons can shift or vanish from their usual places. Vacuum processes can matter. Entire phases of matter can appear that would seem absurd in a household context. There is a broader lesson here about physical laws and human intuition. We tend to trust the middle range of experience too much. We build an emotional picture of what a force is based on the scales at which we meet it. Attraction feels friendly because it is involved in structure and cohesion. Repulsion feels aggressive because it produces sparks and shocks. But nature does not respect those emotional categories. It only respects conditions. If attraction grows strong enough, it can become as disruptive as anything else. It can destabilize as well as bind. It can pull a system into a new regime where the old description fails. It can demand new physics, or at least a fuller version of the old physics than we were previously using. There is also something deeply satisfying about how many safeguards the universe seems to employ before allowing a simple trend to run wild. Electric attraction grows stronger at shorter distances, yes, but quantum uncertainty resists unlimited localization. Strong binding becomes relativistic. Extreme fields awaken the vacuum. Dense matter changes its identity. The theory keeps thickening. At every stage where a careless person might have assumed that more attraction simply means more of the same, nature places a barrier of complexity and says not so fast. It is rather like trying to walk down what looks like a straightforward corridor, only to find that every door opens into a different department entirely. This thickening of the story is exactly what will matter later when we talk about any supposedly maximum charge scale. The idea of a Planck charge or a strongest possible electric strength cannot be understood in the spirit of simple extrapolation. You cannot merely take Coulomb attraction, keep increasing it, and assume the rest of reality stays frozen while you perform the experiment in your imagination. Reality answers back. Fields answer back. Particles answer back. Space-time may eventually answer back as well. Extreme attraction is a conversation, not a monologue. For the moment, though, it helps to remain with a specific picture of opposite charges being drawn together and ask what truly keeps the world from collapsing into the smallest, electrically favourable arrangements. The answer, as we have seen, is never just one thing. It is quantum structure in atoms. It is exclusion principles in many electron systems. It is relativistic corrections in strong fields. It is field-theoretic effects in supercritical regimes. It is changed phases of matter in dense environments. The universe is full of ways to prevent a local trend from becoming a universal disaster, and yet there is no reason to think those protections are merely arbitrary obstacles. They are part of the deeper design of physical law. If design is a word one wishes to use cautiously, attraction becomes extreme not when it somehow breaks the rules, but when it encounters more of them. That is an important distinction. Physics at high intensity is not less lawful. It is more crowded with law. More principles become relevant at once. What looked like a straightforward electric pull reveals itself to be connected to uncertainty, field structure, relativistic energy, and the behavior of the vacuum. That is not a failure of understanding, it is understanding getting more complete. So the next time the word attraction sounds mild, it may be worth remembering that one of the quietest concepts in everyday language becomes, under enough pressure, one of the sternest themes in modern physics. Opposite charges do draw together. They draw together with enough intensity to build atoms, enough precision to make chemistry possible, enough flexibility to support life, and under sufficiently extreme conditions, enough severity to pull quantum theory itself into the conversation. Once that happens, the question is no longer simply how strongly one particle can be bound to another. It becomes a question about thresholds, about when the vacuum begins to participate, about when the old language stops being enough and a more delicate measure of natural strength is needed. That is where another remarkable quantity begins to matter, because after spending time with electric attraction, in its ordinary and not so ordinary roles, we are finally in a position to ask why physicists ever felt the need to invent something as specific and suggestive as the fine structure constant. At this point, the question has changed shape a little. We began with electric force as something familiar but hidden, then moved into the way it can bind matter together, and then into the more serious territory where attraction stops being merely constructive and starts revealing how many other parts of physics are waiting just beneath the surface. Once you get there, it becomes natural to ask a more careful question. If electric force is so important, and if its strength matters so much for atoms, chemistry, radiation, and the structure of matter, how strong is it in a deep, natural sense? Not how strong compared with a hand pulling a drawer open, and not how strong in the practical sense of a laboratory power supply making everyone slightly nervous. something more basic than that. Is there a number built into nature that tells us whether the electromagnetic interaction is weak, strong, or somewhere in a very specific middle ground? There is, and it is one of the most famous numbers in all of physics, though famous in a slightly academic way, like a mathematician who has never once been invited to a noisy party, but is nonetheless known and admired by everyone in the building. It is called the fine structure constant. The name is a little old-fashioned and not especially transparent, which is very much in keeping with physics. It sounds as though it ought to be the title of a Victorian handbook on decorative carpentry, but in fact it is a measure of the intrinsic strength of the electromagnetic interaction in the quantum world. It tells us, in a deep and useful way, how strongly charged particles talk to one another. What makes this number especially remarkable is not only what it measures, but how it measures it. Most constants we meet in physics come with units. They tell you something in meters, kilograms, seconds, or some other human or experimental convention. The fine structure constant is different. It is dimensionless. It is a pure number. That matters enormously, because a pure number is not tied to our choice of ruler, clock, or laboratory habit. If an alien civilization on the other side of the universe had somehow managed to avoid destroying itself long enough to become interested in atomic physics, and if it used completely different units from ours, it would still find the same value for this constant. That gives it a special status. It feels less like a detail of measurement and more like a clue about the structure of reality itself. The fine structure constant tells us that electromagnetic interaction is neither absurdly weak nor disastrously strong at the scales where atoms and light matter most. It sits in a very specific range, and that range is what allows the world to have the kind of stable complexity we take for granted. If the electromagnetic interaction were much weaker, electrons would be held more loosely by nuclei. Atoms would be larger, flimsier, and less decisive in their chemistry. Molecules might form less readily, or behave very differently. If the interaction were much stronger, electrons would be bound much more tightly. Atomic sizes would shrink. Chemical energies would change. The structure of matter could become harsher and less flexible. In either direction, the world would not simply be a mildly adjusted version of the one we know. It could be profoundly different. This is why people sometimes speak of the fine structure constant as expressing a delicate balance. That phrase can sound a bit grand if one is not careful, but there is a very practical truth inside it. The value of this constant affects the size of atoms, the spacing of energy levels, the behavior of light interacting with matter, the patterns of chemical bonding, and many details of what stable matter is like. It is not a decorative extra. It is one of the numbers that quietly shapes the kind of universe that is possible. When physicists look at it, they are not just admiring a neat piece of notation. They are looking at a parameter that helps decide whether matter becomes interesting. The historical reason for the name is also worth mentioning, because it reveals how science sometimes finds its deepest constants while trying to explain what first looked like a technical detail. Early studies of atomic spectra showed that certain lines were split into very close neighbouring lines. This was called fine structure. It was a subtle pattern in the light emitted or absorbed by atoms, especially hydrogen, explaining that splitting required a better understanding of how electrons behave, including relativistic effects and quantum properties that were not yet fully understood in the earliest atomic models. The constant that appeared in this story turned out to be much more than a bookkeeping factor for spectral details. It became one of the defining numbers of quantum electrodynamics and of atomic physics more broadly. That is one of my favourite habits of nature. It hides deep truths inside what first appears to be fussy detail. Someone studies a slight splitting in spectral lines, the sort of thing that sounds like it belongs in a room full of careful people with very clean instruments, and out of that comes a number that helps define the strength of one of the fundamental interactions in the universe. Physics often works like that. What begins as a correction becomes a clue. What begins as a nuisance becomes a landmark. The fine structure constant sits at the meeting point of several ideas we have already been circling. It connects electric charge, quantum behavior, and the speed of light in a way that tells us how important electromagnetic effects are in the quantum world. It is not simply a measure of force in the classroom sense. It is more like a measure of interaction strength in the language the universe seems to use when particles exchange influence. In modern quantum field theory, it helps set the scale for how likely charged particles are to interact through the electromagnetic field. It shows up in calculations of scattering, radiation, energy levels, and many other processes. In that sense, it is less like a single knob marked electricity, and more like a universal volume setting for electromagnetic participation. One of the reasons physicists are so taken with it is that it seems almost suspiciously well chosen. Its value is small enough that certain calculations in quantum electrodynamics can be done as careful expansions, where each additional level of detail contributes a bit less than the previous one. This is very convenient if you enjoy getting answers that match experiment to many decimal places, which physicists do in much the same way some people enjoy perfectly aligned bookshelves. If the constant were much larger, those calculations would become far harder and perhaps much less well behaved. The theory would still exist in some form, but the orderly success of quantum electrodynamics as one of the most accurate theories ever built might look very different. That practical usefulness should not distract from the deeper mystery, though. The fine structure constant has a value. We can measure it extremely well. We can use it with astonishing success. But why does it have that value? That question remains one of the quiet embarrassments and delights of theoretical physics. It is not embarrassing in the sense of failure. It is embarrassing in the sense that nature has handed us a number of enormous importance without including a note explaining herself. We know what the constant does. We know where it appears. We know how to measure it with exquisite precision. But a deeper derivation of its value from first principles remains elusive. This has led some of the greatest physicists to react to it with a mix of admiration and mild exasperation. There is a famous tradition of scientists speaking about this constant, as though it were a message from the universe that everyone agrees is important but no one has yet translated completely. That may be a touch dramatic, but only a touch. A pure number governing electromagnetic strength is exactly the kind of thing that makes physicists both happy and restless. Happy because it is so fundamental. Restless because it is so fundamental. Its role in atomic structure is a good place to appreciate its practical meaning without becoming too lost in formalism. The size of the hydrogen atom, the energies of its bound states, the speed of its electron in the simplest picture, and the spacing of many quantum effects all depend in some way on the strength represented by this constant. It is woven into the architecture of the atom. Change it, and you change the atom. Change the atom, and you change chemistry. Change chemistry, and you change the possibilities for matter, liquids, solids, stars, biology, and everything else that relies on complex stable structures. That is a long chain of dependence, but a real one. There is also an important subtlety here. When we say the fine structure constant measures the strength of the electromagnetic interaction, we should not imagine that it behaves like an ordinary fixed strength in every circumstance without qualification. In modern quantum field theory, interaction strength can depend on energy scale. The effective strength can change slightly as you probe shorter distances or higher energies. The vacuum, once again, is not passive. It polarizes. Virtual particle effects matter, so even this famous constant has layers to it. At ordinary atomic scales, it takes the familiar value we use constantly. At other scales, the effective interaction changes somewhat. This running of the coupling, as physicists call it, is one of those phrases that sounds as though the constant has suddenly taken up cardio, but it means something precise. The apparent strength of the interaction depends on how closely you look. That fact is not a nuisance. It is a sign that empty space participates in physics more actively than common sense first suggests. A charged particle is not just sitting bare in isolation. The surrounding vacuum is full of quantum fluctuation effects that alter how the charge is experienced at different distances. So even here, in a discussion of a constant that seems to promise clean stability, the universe reminds us that stability is layered. There is always more structure than the first telling suggests. Still, at the scale of atoms and chemistry, the fine structure constant serves as one of nature's most important balancing markers. It is small enough that electromagnetic interactions do not crush atomic structure into something much harsher. It is large enough that charged particles bind effectively and atoms have definite size and energy structure. It allows light to interact with matter strongly enough for absorption, emission, and the whole business of seeing and being seen. It helps make radiation and matter mutually intelligible. If it were drastically different, the world might still have interesting physics, but it would not be this world. This becomes especially relevant when thinking about the larger question of how strong electric force can get. The fine structure constant is not itself the final answer to that question, but it tells us that electromagnetic strength is already set by nature in a very specific way at ordinary quantum scales. It is not arbitrary. It is not whatever value happens to be convenient for our textbooks. It is a built-in feature of reality. So when we later talk about Planck charge and truly extreme electric conditions, we are not starting from an undefined concept of strength. We are starting from a universe that already comes with an electromagnetic interaction of carefully fixed character. There is a temptation, when faced with a number like this, to become mystical about it. Some people hear that it is dimensionless and fundamental, and immediately want to assign it the role of cosmic password or secret code, or the answer to a question no one has yet stated clearly. That is probably a little much. Physics does not improve when it begins speaking like an underfunded prophet. Better to stay grounded. The fine structure constant matters because it enters real calculations, explains real measurements, and governs real features of matter and radiation. Its mystery is not that it is spooky. Its mystery is that it is precise, central, and still not fully explained at the deepest level. It is also a useful reminder that not all strong forces are strong in the same way. We have spoken about electric attraction becoming extreme, and later we will speak about Planck scale ideas where gravity and quantum considerations begin to mingle more directly. But the fine structure constant tells us something about the ordinary electromagnetic regime before those more severe scales are reached. It says that even in the day-to-day quantum world, interaction strength is a structured fact, not a vague impression. Nature has chosen a value that permits stable atoms, rich chemistry, and calculable physics. That is already an extraordinary achievement before we ever start asking whether stronger electromagnetic regimes might destabilize the vacuum or press against deeper limits. There is another reason this constant is so beloved, and it has to do with the relationship between theory and experiment. Few areas of physics have matched experiment as precisely as quantum electrodynamics, the theory that describes how light and charged particles interact. The fine structure constant appears throughout that theory, and by measuring related phenomena with immense care, physicists have tested the theory to astonishing levels of precision. That precision is not just a technical triumph. It is a sign that the underlying framework is profoundly right about a large part of reality. When a theory and experiment agree to a ridiculous number of decimal places, the universe is doing more than nodding politely. It is practically saying, yes, that is the idea, carry on. And yet the presence of such success does not remove the sense of delicacy. Quite the opposite, it sharpens it. The better we understand how much depends on electromagnetic strength, the more impressive it seems that the universe sits where it does. Not because someone must have arranged it for our convenience. Physics cannot afford to become too self-congratulatory about human existence. But because the structure of matter really does depend on these values, and small changes in them could have large consequences. Stable complexity is not guaranteed by logic alone. It depends on the particular terms of the physical world. If one wanted a slightly domestic analogy, though with the usual risk of making fundamental physics sound like kitchen management, one might say that the fine structure constant is a bit like the heat setting under a large and delicate meal. Too low and nothing cooks properly. Too high and everything burns or stiffens or becomes unhelpfully dramatic. Somewhere in between, structure emerges. Ingredients interact as they should. The thing holds together. This is not a perfect analogy, mainly because electrons have no interest in your casserole, and the vacuum has never once offered useful cooking advice, but it captures the basic point. The electromagnetic interaction is not merely present, it is set. That setting also interacts with the masses of particles and the strengths of other forces. The universe is not built from one constant alone. What matters is the whole arrangement. But the fine structure constant is one of the clearest examples of how a pure number can shape the possibilities of matter. It stands out because it is dimensionless, because it is so central to electromagnetic phenomena, and because its value has that unsettling quality of seeming at once measured and unexplained. It is like being given the exact key to a lock, and discovering that the door it opens leads into nearly every room of the house. For all these reasons, the fine structure constant is one of the first places physicists look when they want to talk about natural strength without dragging too much human convention into the discussion. It helps strip away the accidents of unit systems and lets us ask what electromagnetism is like on its own terms. Once you do that, the force no longer appears merely as sparks, fields, and classroom demonstrations. It appears as a fundamental interaction with a built-in intensity that shapes atoms from the inside out. And that brings us closer to the threshold we're heading for. Because if nature already assigns electromagnetism a specific interaction strength in the quantum world, then any attempt to ask how far electric force can be pushed has to reckon with that fact. The story cannot just be about bigger charges and shorter distances in the abstract. It has to involve the dimensionless strength of the interaction, the way fields behave at higher energies, the response of the vacuum, and eventually the place where electromagnetic ideas meet the deeper scales associated with Planck units. The fine structure constant, in other words, is the calm middle of the story. It is the measured, successful, stable expression of electromagnetic strength before things begin to turn severe. And precisely because it is so stable and so central, it sets the stage for the next question, which is why physicists felt the need to define a natural scale of charge at all, and what it means when they say that somewhere beyond our familiar atomic world there is a quantity called the Planck charge waiting like a boundary marker at the edge of the map. Once a constant like that is on the table, something almost inevitable happens in physics. The mind starts asking whether the value we're used to is large or small in any deep sense, or whether it only feels that way because we have chosen a particular human scale for measuring things. That is one of the reasons Planck units were invented in the first place. They are an attempt to stop talking in terms that belong to us, and start talking in terms that belong, as much as possible, to nature itself. Instead of meters because we are medium-sized creatures on one planet, or seconds because our clocks divide time in historically convenient ways, Planck units are built from the constants that seem to govern reality at the deepest level we know how to describe. In that family of natural scales there is a Planck length, a Planck time, a Planck mass, a Planck energy, and among them sits the Planck charge. And the reason it matters is not because it is the charge of some mysterious particle waiting behind a curtain, but because it tells us what charge looks like when we stop using ourselves as the reference point. That is an important shift. Most of the time, when we think about charge, we do so in relation to the electron. The electron carries the most familiar basic unit of charge in ordinary matter. Chemistry is built around it. Electricity in materials is often about its movement. Static shocks, currents in wires, bonding in atoms. Much of the practical electrical world is electron territory. so it is very easy to treat the electron charge as though it were automatically the natural scale of all things electric. But physics has a habit of asking whether the quantities that matter most to daily life are also the ones that matter most to the structure of theory. Often the answer is only partly. The electron charge is fundamental in one sense, but the Planck charge asks a different question. It asks what scale of charge emerges when you combine the deepest constants associated with relativity, quantum theory, and gravity into a single natural unit. As soon as you do that, something rather interesting happens. The Planck charge does not turn out to be absurdly larger than the electron charge. It is larger, certainly, but not by some ridiculous number of orders of magnitude. It is only a few times larger in magnitude. That can be surprising at first. After all, the Planck scale has a reputation for sounding impossibly remote, like the sort of place where physics wears a very stern expression and refuses to answer straightforward questions. One might expect the natural unit of charge associated with that realm to be fantastically huge compared with anything atomic. But it is not. It is bigger than the charge carried by the electron by only a modest factor. That fact is not trivial. It tells us that the ordinary charge of the electron is not wildly far from the natural charge scale set by the deeper structure of physical law. And that brings us back to the fine structure constant in a satisfying way. The fine structure constant is, in effect, a measure of how the electron charge compares with a natural electromagnetic scale. It tells us that the electron's charge is smaller than the Planck charge, in just such a way that electromagnetic interactions in the atomic world are significant but not overwhelming. If the electron carried something more like the Planck charge, the electromagnetic interaction at ordinary quantum scales would be much more severe. Atomic physics would be harsher. The careful balance that allows chemistry, stable atoms, and manageable quantum electrodynamics would look very different. So the Planck charge matters partly because it gives us the missing backdrop against which the electron charge can be understood. It tells us what ordinary charge is small relative to. That may sound abstract, but it is actually one of the most useful clarifications in the whole discussion. The Planck charge is not important because objects in the universe are forbidden from having more net charge than that. It is not a cosmic speed limit for charge in the simple sense. A larger object can certainly have a total charge greater than the Planck charge. A black hole can, in principle, carry much more than that depending on its mass and circumstances. A charged dust cloud or macroscopic device can have a net charge exceeding it. So if one imagined the Planck charge as the largest charge nature allows, one would be misunderstanding the point. It is not a universal maximum for every situation. It is a natural unit, a benchmark. It matters because it tells us where charge stops looking like a merely practical quantity and starts looking like a participant in the deeper scale setting of the laws themselves. Another way to say it is this. The Planck charge marks the scale at which electric interaction ceases to feel parametrically small when compared in natural units. In ordinary atomic physics, the electron charge is large enough to matter enormously, but still small enough that the electromagnetic coupling is not of order, one in the most severe possible sense. There is room for controlled theory. There is room for expansion, approximation, stable structures, and the remarkable success of quantum electrodynamics. The Planck charge points to the place where that relative smallness disappears. It is the charge scale at which the bookkeeping of electromagnetism begins to look maximally serious in natural terms. That matters for several reasons. One is conceptual honesty. When physicists ask about extreme electric fields or the strongest electric force that can be meaningfully discussed, they need a way to separate the accidents of our chosen unit system from the real structure of the problem. The Planck charge provides that. It says that if you want to talk about charge in a form that does not depend on whether you use one set of practical electrical units or another, here is the scale that nature itself suggests. It is a translation from the local dialect of engineering into the deeper grammar of fundamental physics. It also matters because it links electromagnetism to gravity in a very quiet but very deep way. The Planck unit system is built from constants that include the strength scale of gravity in its relativistic quantum role. That means the Planck charge is not just an electromagnetic curiosity. It is a sign that charge can be discussed in the same natural language as Planck mass, Planck length, and Planck time. Once that happens, you're no longer treating electromagnetism as a separate compartment of physics with its own isolated measuring sticks. You're placing it on the same conceptual map as the scales where gravity, quantum mechanics, and relativity all begin to matter together. In other words, the Planck charge matters because it helps locate electromagnetism on the road toward quantum gravity. That road is not short, and it is certainly not fully paved, but the marker is real. Suppose you ask how intense an electric interaction could become if charge were concentrated at very small scales. Coulomb's law by itself lets you imagine the force growing larger as distance shrinks and charge increases. But once you approach sufficiently extreme regimes, you can no longer talk as though electric force were taking place in a world where gravity and quantum structure remain politely out of frame. The Planck charge reminds you of that. It is one of the warning signs that says this problem eventually belongs to the unified high-energy frontier, not just to classroom electrostatics. There is also a more specific insight hiding here. Because the Planck charge is only modestly larger than the electron charge, the smallness of the fine structure constant does not come from charge being absurdly tiny in every imaginable natural sense. It comes from a more precise numerical relationship. The electron's charge is smaller than the natural Planck scale in just the right way to make electromagnetic interaction strong enough for atoms and chemistry, but still perturbative enough for our theories to behave so well at accessible energies. That is a very elegant outcome. It means the electromagnetic world we know is neither feeble nor maximal. It is intermediate in a very disciplined sense. This intermediate character is easy to miss, because our language about electric force tends to swing between the practical and the dramatic. We speak of tiny currents in electronics on one hand and lightning on the other. Both are real, but neither directly tells you how charge should be measured in a theory that wants to compare electromagnetism with gravity at the deepest scales. The Planck charge does that. It strips away the emotional contrast between battery and storm and instead asks a more neutral question. How large is charge when nature chooses the units? The answer does not replace the electron, it contextualizes it. Context is really the heart of why this quantity matters. Without it, the question of maximum electric force can become muddled. One person imagines piling more charge onto a particle. Another imagines stronger electric fields in a region of space. Another thinks in terms of the energy required to probe shorter distances. Another imagines black holes with charge. All of these are related, but not identical. A natural unit like the Planck charge does not solve every version of the problem, but it tells you where the conversation becomes serious. It tells you when charge stops being merely a familiar attribute of matter and starts becoming one of the deep inputs to natural scale setting. There is a subtle but important philosophical benefit here as well. Physics is always trying to distinguish between things that are fundamental and things that are conventional. A meter is conventional in the sense that its exact human definition could have been packaged differently. A second has a conventional aspect as well, even though it is now tied to very precise physical standards. But a pure comparison between natural quantities, especially when it produces a dimensionless statement, feels less accidental. The Planck charge contributes to that effort. It is part of the attempt to say not just how much charge in our laboratory language, but how much charge in the language the universe itself seems to prefer. That is not mysticism. It is simply a search for the least arbitrary way of speaking. The importance of the Planck charge also becomes clearer when you think about field strength, rather than just total charge. A total charge spread gently over a large object may not do anything especially severe. A smaller charge compressed into a tiny region can create a much more intense field. The Planck charge Being part of the Planck unit system hints at the regime where such compression would start to intersect with the scales of quantum gravity. It does not say every occurrence of that much charge is catastrophic. It says that if you combine natural charge with natural length and time scales, you're entering territory where ordinary separations between forces and theories may no longer be trustworthy. It is a boundary marker, not an alarm bell that rings in all contexts. That distinction matters a great deal. One of the most common misunderstandings about Planck scale ideas is to treat them as though they were dramatic thresholds that ordinary things are constantly threatening to cross. In reality, Planck scales usually matter when several forms of extremeness arrive together. Very high energy, very short distance, very strong curvature, very intense concentration. These are the sorts of conditions that start forcing gravity, quantum mechanics, and field theory into the same room. The Planck charge is part of that family. On its own, as a number, it is not the end of the story, but it tells you how charge should be measured when the full story starts to matter. There is another reason physicists care about it, and that is because natural units often reveal hidden simplicity. Equations that look crowded and arbitrary in ordinary units can become much cleaner when written in Planck form. Relationships that seem to involve many separate constants turn out to be saying something straightforward once the natural scales are used. The Planck charge participates in that simplification. It helps show that the small electromagnetic coupling of the electron is not just a random engineering number, it is a ratio. And ratios are often where the deepest understanding begins. Think of it this way. If someone tells you the height of a hill in inches, you can know the number without gaining much intuition. If they tell you the hill is only a small fraction of a mountain range, suddenly you understand where it belongs. The Planck charge does something like that for the electron charge. It tells you not just its value in practical units, but its place in the natural landscape. The electron is not carrying the maximal natural charge. It carries a smaller one, by a factor that turns out to control the strength of the electromagnetic interaction in a beautiful and measurable way. That is the sort of insight that makes a constant feel less like a fact to memorize, and more like a structural relationship. It also feeds directly into questions about why the electromagnetic interaction is what it is. If the Planck charge provides a natural reference scale, then the smallness of the electron charge relative to that scale becomes one of the great explanatory targets. Why this ratio? Why this degree of coupling and not another? Why is the universe set up so that charge is strong enough to build atoms and chemistry, but not so strong that everything is driven into much more violent binding or a badly behaved theory? The Planck charge does not answer those questions, but it tells us how to phrase them sharply. That sharpness is especially useful when moving toward more extreme topics like pair creation in strong fields, vacuum instability, or charged black holes. In all of these cases, what matters is not just that there is charge, but how charge compares with the natural scale set by the full structure of the theory. A black hole, for example, can in principle carry charge, but there are meaningful limits to how much charge it can have relative to its mass if it is to remain a black hole rather than becoming something more problematic. Natural charge scales help make those statements clean. They let us compare gravity and electromagnetism without getting lost in arbitrary units. There is something rather elegant about the fact that the Planck charge sits at an intersection of humility and ambition. Humility because it reminds us that our usual practical reference points are local habits, not the final language of physics. Ambition because it shows that we really can build a unit system out of the basic constants of the world and ask what charge means there. That is one of the grand projects of theoretical physics in miniature, not just measuring what we happen to encounter, but finding the scales at which nature declares its own preferences. Of course, this does not mean the Planck charge is the final answer to how strong electric force can get. It is better thought of as a compass than as a destination. It points toward the regime where the question becomes genuinely fundamental. It tells us when electromagnetic strength must be discussed alongside the other deepest scales we know, It helps translate the ordinary story of charge into the language of ultimate limits. But to turn that into a statement about force, one more step is needed. Charge alone is not force. Distance matters. Field strength matters. Energy concentration matters. The geometry of space-time may matter. Vacuum response may matter. The Planck charge matters because it tells us what natural charge is, but the question of how strong electric force can truly become requires us to ask what happens when that charge participates in the most extreme conceivable circumstances. And that is why this quantity deserves its place in the story. It is not a curiosity tucked into the back of a theoretical handbook. It is a bridge. It connects the familiar world of electrons and chemistry to the natural unit system where electromagnetism is measured against gravity and quantum structure together. It reveals that the electron's charge is significant but not maximal in the deepest natural sense. It helps explain why the fine structure constant is the kind of number it is. It tells us where the ordinary language of electric force begins to give way to a sterner, more universal one. Once that bridge is in view, the next question becomes unavoidable, because now that charge has a natural scale, we can finally ask what it would mean to measure electric force itself, at the edge of what nature allows. Now that charge has a natural scale, the next question becomes more demanding in exactly the right way. It is one thing to say that the universe gives us a natural unit of charge, a reference point that helps us stop thinking only in terms of batteries, sparks, and electrons moving through copper. It is another thing entirely to ask how that charge would translate into force under the most extreme conditions nature can meaningfully accommodate. Because force is never just charge by itself. Force is charge in relation to distance, and distance turns out to be the part of the story that becomes truly severe. A moderate charge at a generous distance may behave politely. The same charge brought closer becomes far less diplomatic. So when we ask about the strongest electric force nature allows, we are really asking about a convergence of limits. How much charge, compressed how tightly, acting across how small a region, before the whole description begins to strain. That last phrase matters, because nature does not hand out maximum values in the form of a tidy sign on a gate, saying no further beyond this point. Physics is more subtle than that. It gives us scales where our theories stop behaving as though they can be trusted independently. It gives us thresholds where one kind of description starts to interfere with another. It gives us regions where the very meaning of a question becomes more delicate. The strongest electric force nature allows is not necessarily a single number sitting in a vault, somewhere waiting for a patient enough physicist to retrieve it. It is more like a natural frontier. If you try to measure electric force at greater and greater intensity, you eventually reach a place where electromagnetism, quantum theory and gravity all begin to insist on being included in the conversation at the same time. To see why, it helps to begin with the ordinary logic of electric force and then keep tightening it. In the classical picture, two opposite charges pull toward one another more strongly, when the charges are larger and when the distance between them is smaller. That much is straightforward. So one might naively imagine that the strongest possible electric force would come from taking the largest meaningful charge and the smallest meaningful distance and simply combining them. That intuition is not wrong so much as incomplete. It points in the right direction, but it ignores the fact that very small distances are not passive. Space at those scales cannot simply be treated as a featureless backdrop. The vacuum is active. Quantum fluctuations matter. Energy density matters. Space-time may cease to behave like the smooth stage we're used to. So the act of measuring the strongest electric force is already entangled with the act of deciding what counts as a physically meaningful smallest distance. That is where Planck units become useful again. If the Planck charge gives us a natural scale for charge, then the Planck length gives us a natural scale for distance at which our ordinary concepts of space are expected to become uncertain, or at least incomplete. Put those two ideas together, and a very striking thought emerges. If you imagine electric interaction using a natural charge acting across a natural minimum length, the resulting force lands on the same scale as the natural force scale associated with the Planck regime more broadly. In other words, when charge and distance are both pushed to their natural extremes, electric force becomes comparable to the deepest force scale we know how to construct from the constants of nature. That is not an accident of notation. It is a clue. It tells us that the strongest electric force is not merely an exaggerated version of classroom electrostatics. It belongs to the territory where all the foundations start touching. This is one of those points where the question becomes conceptually more interesting than any single number one could quote. Of course, there is a staggering scale associated with this natural force, and it is unimaginably larger than any force encountered in daily life. A human hand, a rocket engine, a collapsing building, a lightning bolt, all of these are gentle and provincial by comparison. But the more important point is that this natural electric force is not something one expects to isolate cleanly in a laboratory the way one measures a spring or a voltage difference. It is the scale at which the very notions of particle field and space-time geometry begin to overlap so strongly that a simple force law is no longer enough by itself. Even before reaching anything so remote, nature gives us warning signs. We have already touched on one of them in a softer form. If an electric field becomes strong enough, the vacuum can respond by producing particle pairs. What looked like empty space starts participating. This means that even well below the full Planck regime, electric intensity can trigger self-limiting behavior. A sufficiently strong field does not just sit there growing forever like a number in a thought experiment. It begins to discharge itself through quantum processes. The field can pull real particles out of the vacuum. In that sense, nature starts pushing back before the deepest possible limit is reached. Electric force is not free to become arbitrarily intense without consequences. The world notices. That is an important correction to any simple notion of maximum strength. There are at least two different ideas in play. One is the absolute natural scale suggested by Planck units, where the force would be as large as it can meaningfully be before our current theories need something deeper and unified. The other is the practical onset of new physics that prevents electric fields from being increased cleanly in an ordinary way, such as vacuum pair creation. These are not the same thing. A field may become unstable and begin producing particles long before one has reached the Planck frontier. So when we talk about the strongest electric force nature allows, we have to ask whether we mean the strongest force that can exist even momentarily in principle, the strongest field that can remain stable, or the strongest interaction that can be described without full quantum gravity. Those are related questions, but not identical. The reason this matters is that electric force is not merely a strength written on an object. It is an interaction unfolding in a context. A huge total charge spread over a very large object may not produce an especially extreme local force. A smaller charge concentrated into a tiny region may create a far more intense field. A charged black hole introduces one set of constraints. A supercritical nucleus introduces another. A laser field approaching vacuum breakdown introduces yet another. Each case teaches something about electric strength, but none of them by itself defines the final answer. Measuring the strongest electric force nature allows means learning how these different versions of extremeness talk to one another. Perhaps the cleanest conceptual path is this. First, identify a natural charge scale. Second, identify a natural distance scale. Third, ask what kind of force results if those scales meet. The answer is astonishingly large, but more importantly, it is natural rather than arbitrary. It does not depend on the size of a laboratory or the habits of an engineer. It comes from the constants themselves. In that sense, it is the best candidate we have for a deepest electric force scale. But the reason physicists treat it with caution, rather than triumph, is that once you are using Planck length as part of the setup, you have already stepped into a region where the ordinary idea of distance may need to be revised. You're measuring at the edge of the map using the map's own warning label. There is something almost paradoxical about that. the natural way to estimate the strongest electric force points us to a scale where force as a classical concept may itself be under pressure. Force is a useful and beautiful idea in ordinary mechanics and field theory, but at the deepest scales, one often shifts toward talking about action, scattering, field amplitudes, energy densities, and quantum geometrical effects. So even as we approach the sharpest answer physics can currently suggest, the familiar language begins to blur. The strongest electric force is not just very large, it is the kind of largeness that forces us to reconsider the language in which largeness is being described. Still, the natural scale remains meaningful. It tells us that if electric interaction were concentrated as much as the known constants permit, before the present framework gives way, the result would be a force of Planck order. And that phrase, Planck order, is one of physics' quiet ways of saying beyond this point your confidence should become very well mannered. It is not a dismissal, it is an invitation to honesty. We can estimate, we can compare, we can see how the known constants conspire. But we cannot yet claim to possess a complete and experimentally settled theory of that regime. There is another angle on this that makes the issue feel more tangible. Consider what it would mean to create an electric field strong enough to pull apart the vacuum. This is already an immense feat, one far beyond ordinary static electricity, and even beyond many of our most powerful present technologies. At that point, the field is no longer simply a background condition for matter. It becomes a participant in creating matter. The vacuum does not tolerate the field's intensity passively. Particle pairs appear. Screening occurs, the field partially discharges itself. This is nature's way of saying that electric strength cannot simply be dialed upward forever without changing the content of the world. A sufficiently strong field changes what the world contains. That is a profound principle, and it helps prepare the mind for the Planck scale version of the story. At still greater intensity, one should not expect only more pair creation. One should expect the very distinction between field in space and geometry of space to become less clean. Energy itself gravitates. A truly enormous electric field carries energy density, and that energy density contributes to space-time curvature. So the stronger the field becomes, the less justified we are in pretending that gravity can be ignored. This is why the strongest electric force nature allows is ultimately not an electromagnetic question alone. It is a question about the whole architecture of physical law. The field bends the stage on which it appears. Charged black holes make this especially vivid. In general relativity, a black hole can carry electric charge, and the charge changes the structure of the surrounding space-time. But there is a limit to how much charge such an object can sustain relative to its mass, if it is to remain an ordinary charged black hole. Push the charge too far relative to the mass, and the geometry becomes problematic in ways that suggest the object cannot be formed or maintained by ordinary physical processes. This is another place where electric strength meets gravitational structure. The theory itself tells you that charge does not get an entirely free hand when gravity is included. There are bounds, balances, and extremal conditions. Nature is once again less permissive than a simple extrapolation would suggest. Even here, though, one has to resist the temptation to think there is a single universal ceiling in the everyday sense. A large black hole can hold a larger total charge than a small object simply because its mass is larger. So the relevant question is not always total charge or even total force, but the comparison between charge, mass, and scale. That is why Planck units remain so useful. They let us compare unlike things in a common language. A Planck charge concentrated at Planck length gives a natural benchmark. A black hole's charge compared to its mass gives another kind of benchmark. A vacuum breakdown field gives another. These are different windows onto the same deep issue. How far can electric intensity be pushed before another part of nature takes over the conversation? There is also a more subtle meaning to the word measuring in this context. We're not just asking how nature sets a limit, we're asking how physicists come to know that such a limit or scale exists. The answer is a mixture of dimensional reasoning, theoretical consistency, and known physical thresholds. Dimensional reasoning tells us what natural combinations of constants define scales of charge, length, time, and force. Theoretical consistency tells us that at certain combinations of these scales, our separate theories start colliding. Known physical thresholds, such as pair creation in strong fields, tell us that long before the ultimate scale is reached, electric intensity already triggers new behaviour. Taken together, these strands let us speak meaningfully about the strongest electric force without pretending we have bottled it in a device and taken a tidy reading. This distinction between direct measurement and theoretical inference is common in the deepest parts of physics. We have not held a Planck length next to anything in the way one holds a ruler to a table. We have not watched a Planck force bend a laboratory instrument while someone writes down the result. But that does not make the scale fictional. It makes it theoretical in the best sense. It is inferred from the way the known constants fit together, and from the recognition that certain combinations define unavoidable frontiers. Physics often proceeds this way. It maps regions long before it visits them, and there is good reason to trust that map, even if parts of the terrain remain misty. The same theoretical framework that gives us these natural scales also successfully describes an enormous range of observed reality. Quantum electrodynamics works with breathtaking precision at accessible energies. General relativity works with extraordinary success in gravitational settings. Quantum field theory predicts vacuum effects and thresholds that fit beautifully with what we know. The trouble is not that our theories are untrustworthy. The trouble is that they are each so trustworthy in their own domains that we know exactly when their separation starts to feel artificial. The strongest electric force nature allows lives in that overlap region. There is something deeply satisfying about how the story holds together. At modest scales, electric force shapes atoms, molecules, chemistry, matter, and life. At stronger scales, it strips atoms, drives plasmas, powers lightning, and governs intense radiation processes. Stronger still, it can destabilize the vacuum through pair creation. Push it conceptually to the natural limit defined by charge and distance at Planck scale, and it reaches a force comparable to the deepest natural force scale we can construct. The progression is not random. It is layered. Each new stage does not erase the earlier one. It contains it and then complicates it. This layered structure is also why it would be misleading to answer the original question with just a dramatic one-line claim. One could say, the strongest electric force nature allows is of Planck scale, and that would capture the deepest natural benchmark. But without everything that surrounds that statement, it sounds sharper and simpler than it really is. Nature starts protesting earlier through vacuum effects. Stability matters. Geometry matters. Total charge is not the same as local field intensity. Natural units point toward the deepest scale, but the road to that scale is lined with warning signs, not open highway. The real answer is therefore more interesting than a single number. It is a hierarchy of resistance. As electric force grows, more of nature pushes back. That is perhaps the most important thing to carry forward. The strongest electric force is not merely the greatest push or pull between charges, it is the point at which the distinction between electric interaction and the rest of fundamental physics begins to break down. It is measured not only by how hard one charge can act on another, but by when fields create particles, when energy densities matter gravitationally, and when the geometry of space-time may itself refuse to remain a passive background. Measuring that strongest force is therefore less like finding the largest object in a room, and more like discovering the point at which the walls, floor, and air all start participating in the answer, and once you reach that realization, a further consequence becomes unavoidable. If the natural strongest electric force lives at a scale where all our separate classical pictures begin to crowd together, then the next real issue is not the force itself, but the breakdown of the framework that led us there. Because classical electrostatics is elegant, useful, and astonishingly successful within its proper range. But it was never meant to carry the full burden of reality at the most extreme scales. So after asking how strong electric force can get, the next thing we must face is what starts to fail first when we try to push the classical picture too far. There is a comforting quality to classical physics when it is working well. It speaks with confidence. Charges attract or repel, fields spread through space, forces weaken with distance in a clean and orderly way. Energy is conserved. Motion follows from causes that can be stated precisely. If you stay within the right range of problems, this picture is not only useful, it is beautiful. It explains why rubbed objects cling, why lightning discharges, why conductors and insulators behave differently, why charges rearrange themselves in response to one another, and why the electric world can be described with such elegance. For a long time, it looked as though the language of classical electricity and magnetism might be complete enough to handle almost everything. And to be fair, for many ordinary purposes it still is. The power grid does not stop functioning because quantum theory exists. A radio does not fall silent out of respect for relativity. Classical ideas remain deeply reliable across a huge range of human experience. But reliability in one range is not the same as universality. That is one of the hardest and most important lessons in physics. A theory can be excellent, exacting, and profoundly successful, and still not be the last word. It can describe a wide domain with extraordinary skill, and yet begin to fray when pushed beyond the conditions that first made it seem so secure. Classical physics, especially in its treatment of electricity, runs into that kind of trouble in several places. Not all at once, and not in a dramatic collapse, but in a series of increasingly serious tensions. The more closely one looks, and the more extreme the conditions become, the more the classical picture starts to look like an approximation rather than a foundation. One of the earliest and clearest places this happens is in the atom. If you describe the electron and nucleus in purely classical terms, trouble appears almost immediately. The electron is negatively charged, the nucleus positively charged, and opposite charges attract. So far, so good. One might picture the electron moving around the nucleus the way a planet moves around the sun, bound by an inward force. That picture is seductive because it feels familiar. It takes something new and dresses it in an old costume. But a charged particle in motion, according to classical electrodynamics, should radiate energy. An orbiting electron is accelerating, even if its speed remains steady, because its direction is constantly changing. And an accelerating charge should emit electromagnetic radiation. That means the electron should lose energy, spiral inward, and collapse into the nucleus in a tiny fraction of a second. Clearly that does not happen. Atoms exist. Matter exists. The chair does not dissolve into a glowing crisis under the weight of its own electrical bookkeeping. So the classical picture, while tempting, cannot be right in this domain. It is not that classical physics gives a slightly inaccurate answer. It gives the wrong kind of answer altogether. It predicts instability, where the world displays stability. That is one of the strongest possible signals that a theory has reached the edge of its proper territory. When the theory says the world should fall apart and the world remains politely assembled, it is time to look elsewhere. Quantum mechanics enters at exactly that point, not as a decorative correction, but as a replacement for the classical atomic picture. The electron does not simply orbit as a tiny charged bead. It occupies allowed quantum states. Its energy comes in discrete levels. The atom is stable because the electron cannot just slide inward continuously, the way a classical object would. This is the sort of failure that teaches humility. Classical electromagnetism was not nearly wrong about electricity in the atom. It was fundamentally incomplete. It needed a new framework. A similar tension appeared in the study of light and radiation. Classical physics treated radiation as something that could vary continuously and that worked well in many settings. But when physicists tried to understand the spectrum of radiation emitted by hot objects, they ran into a deep problem. Classical reasoning suggested that hotter objects should pour more and more energy into shorter wavelength modes without limit. The predicted result was absurd. The amount of energy at the shortest wavelengths should become infinite. This came to be known as the ultraviolet catastrophe, which is one of those rare scientific phrases that manages to be both accurate and unexpectedly theatrical. Nature once again declined to behave catastrophically in the prescribed manner. Real hot objects do not emit infinite energy. Their radiation spectrum has a definite shape, one that classical theory could not explain. The fix was not a minor adjustment. It required the introduction of energy quanta. Light and the oscillators that exchange energy with matter do not behave as though energy were infinitely divisible in the classical sense. That insight was one of the starting points of quantum theory. So here too, the classical framework begins to fail, not because the mathematics is clumsy, but because the world itself insists on discreteness, where classical intuition expects continuity. Electricity is woven deeply into that story as well. Once light interacts with charged particles, once atoms absorb and emit radiation, once electrons respond to electromagnetic fields, the old classical language starts showing cracks. The photoelectric effect is another famous example. Classical wave theory suggested that shining brighter light on a metal should eventually supply enough energy to liberate electrons, regardless of the light's colour, provided one waited long enough. But experiments show that the effect depends crucially on frequency. Below a certain threshold, no electrons are emitted no matter how intense the light is. Above that threshold, electrons appear promptly. Once again, the world chose quantum behaviour over classical expectation. Electromagnetic interaction at small scales did not obey the smooth, continuous logic that classical theory would have preferred. These examples may sound like the usual greatest hits of early quantum history, and in a sense they are, but they matter here for a reason. They show that classical physics begins to break not only when things become large, violent, or obviously exotic, but also when one enters the intimate domain of charged matter and radiation. The atom, the hot object, the illuminated metal surface, all are enough to reveal that the classical account of electric phenomena is not the whole truth. If that is already the case in familiar microscopic settings, then one should be even more cautious when asking about the strongest electric force nature allows. The more intense the fields, the less reason there is to trust the classical picture without qualification. Another place where classical electrodynamics starts to look strained is in its treatment of the charged particle itself. In many calculations, one talks about a point charge, something with charge concentrated at an exact point in space. This is mathematically convenient and often practically useful. But if one takes the idea too literally, a problem appears. The electric field around a point charge becomes stronger and stronger the closer one gets to the location of the charge. If the charge truly occupies an exact point, the field intensity near that point becomes unbounded. So does the energy associated with the field. The self-energy of a point charge in classical theory diverges. In plainer language, the particle's own field appears to contain an infinite amount of energy if the particle has no size at all. That is not the sort of thing one likes to leave lying around in a theory and pretend it is good furniture. It may be tolerated as a sign that the model is approximate, but it is not satisfying. Physicists tried various ways of softening the problem historically, sometimes imagining that the charge was spread over a tiny sphere rather than concentrated at a strict point. But those fixes quickly become awkward. What holds the charge distribution together against its own electric repulsion? Why should the radius be what it is? Why does the electron, which appears point-like in high-energy experiments, not reveal some simple classical internal structure? The deeper one pushes, the less the classical picture of a charged object resembles something self-consistent. Quantum field theory approaches this in a very different way, and though its own methods are mathematically demanding and not free from conceptual headaches, it at least reframes the problem more successfully. The electron is not best understood as a tiny classical charged sphere. It is a quantum excitation of a field, and its interactions with the electromagnetic field must be treated accordingly. Even there, infinities appear and must be handled by renormalization, which is itself one of the great technical and philosophical adventures of modern physics. But the point for our story is simpler. Classical electricity begins to break as soon as one asks too literally what a charged particle is and how its own field behaves at arbitrarily short distance. There is also the issue of radiation reaction, which sounds harmless enough until one looks at it closely. If an accelerating charge emits radiation, then conservation of energy suggests the charge's motion should in some way feel the back reaction of that emission. The particle should not only generate radiation outward, it should also experience a kind of self-influence because of the energy it is losing. Writing down a fully sensible classical equation of motion for this turns out to be surprisingly difficult. Some classical formulations lead to pathological behaviour. A charge may appear to accelerate before an external force is applied, or exhibit runaway solutions where the motion increases absurdly on its own. These are not minor inconveniences. They are signs that the classical account of a radiating charged particle is conceptually unstable under close inspection. Once again, this does not mean classical electrodynamics becomes useless. It remains enormously effective in practical settings, from antennas to circuits to wave propagation. But when one tries to force it into the deepest questions about the individual charged particle, or about self-consistent extreme motion, it begins to show cracks. It was built to describe fields and charges in the regime where continuum reasoning works well. It was not built to be the final microscopic theory of matter and radiation. Relativity introduces another pressure point. Classical electrostatics works nicely when charges are stationary or moving slowly. But if charges move near the speed of light, this simple static picture is no longer enough. Electric and magnetic fields become aspects of a unified electromagnetic structure that depends on the observer's state of motion. Simultaneity becomes frame-dependent. Energy and momentum take relativistic form. Even the notion of force must be handled more carefully. This is not yet a failure in the catastrophic sense, because classical electromagnetism can be made relativistically consistent through Maxwell's theory. But it does mean that the simplest classroom form of electric force is only a partial image. Once velocities become extreme, the old intuition of fixed charges pulling and pushing across a quiet stage becomes too narrow, and then there is the vacuum. Classical physics treats empty space, at least in most ordinary contexts, as a passive arena. Fields may live in it, waves may cross it, but the vacuum itself does not fluctuate, polarize, or spontaneously produce particles. Quantum theory changes that. In quantum electrodynamics, the vacuum is not empty in the classical sense. It has structure. Virtual processes contribute to the effective behavior of fields and charges. A strong enough electric field can destabilize the vacuum and produce real particle pairs. This is a profound departure from classical thinking. In classical theory, stronger field simply means stronger field. In quantum theory, sufficiently strong field means the medium of emptiness itself begins to participate. That threshold marks a very clear place where classical reasoning fails. If you imagine raising the electric field forever and treating the vacuum as inert all the while, you are making a mistake. Nature intervenes. Particle creation, screening, and back reaction enter the scene. The field does not remain an isolated classical object. It changes what exists in the region. This is exactly the sort of effect that makes the question of maximum electric force so delicate. The closer one gets to extreme intensity, the less one can treat the field as a fixed classical background. There is also the problem of continuity itself. Classical field theories assume a smooth space-time continuum. Fields are defined at each point. Distances can, in principle, be made arbitrarily small. That works astonishingly well across most observed scales. But if one pushes toward the Planck regime, the idea of arbitrarily fine, smooth structure begins to look doubtful. quantum gravity is not yet complete, but nearly every serious attempt to think about physics at that scale suggests that our ordinary classical picture of space-time cannot remain untouched. Whether space becomes discretized in some manner, or geometry fluctuates violently, or something even stranger occurs, the smooth classical backdrop is unlikely to survive unchanged. This matters because electric force depends on distance, and distance is only as meaningful as the geometry in which it is measured. If space-time itself becomes uncertain or dynamical in a genuinely quantum way, then the idea of two charges separated by an exact tiny interval becomes less straightforward. Classical electrostatics presumes a clean geometry in which force laws can be applied. At the deepest scales, that geometry may no longer be available in the form we have assumed. So classical physics begins to break not only in matter and radiation, but in the stage on which both are described. There is a temptation, at this point, to treat classical theory as old furniture that ought to be moved out of the room now that quantum theory and relativity have arrived with more fashionable opinions. But that would be unfair. The proper lesson is not that classical physics is wrong in the crude sense. It is that it is conditional. It gives the right account where the world is coarse enough, calm enough, or averaged enough for its assumptions to hold. It is like a map of a city that is perfectly useful for walking to the station, but hopeless if you're trying to understand the molecular structure of the pavement. The map did not fail. You asked the wrong question of it. Still, when discussing electric force near its possible upper limits, it becomes essential to know where that map stops being enough. Classical force laws are excellent guides to the middle ranges of reality. They are not judges of the far frontier. The atom already showed that. Blackbody radiation showed that. Point charge self-energy showed that. Radiation reaction showed that. Vacuum instability showed that. Relativistic motion complicates it further, and the likely quantum nature of space-time undermines the clean geometric assumptions beneath it all. What is especially striking is that classical failure rarely arrives as a single contradiction announced by a trumpet. More often, it comes as a pattern of discomforts. Here the atom is unstable when it should be stable. There the spectrum diverges when it should remain finite. Elsewhere, the charge has infinite self-energy, or the motion of a radiating particle becomes pathological, or the vacuum behaves in ways the theory did not foresee. The cumulative message is what matters. Classical theory is a magnificent approximation, but it is an approximation nonetheless. That is why the strongest electric force cannot be treated as though it were the final extreme point of a purely classical curve. The curve itself is only part of the story. Before the force reaches its deepest natural benchmark, classical reasoning has already been corrected, replaced, or supplemented several times. At small scales, quantum mechanics reshapes the structure of matter. In strong fields, quantum field theory reshapes the vacuum. At high energies and severe concentrations, relativity and gravity refuse to remain absent. The breakdown is not a single crack, it is a change in language, and that change in language is exactly what we need next. Because once classical physics has reached the edge of its authority, the obvious question is what takes over? What kind of description replaces a world of smooth fields in passive space and charged particles that can be treated as tiny classical objects? How do we talk about electric intensity when the vacuum itself responds, when particles are excitations of fields, and when emptiness has its own tension and structure? That is the point where the story moves from classical breakdown into the richer and stranger territory of quantum fields, vacuum tension, and the severe limits that begin to appear when electric strength is pushed far enough that the universe stops acting like a silent container and starts answering back. Once the classical picture begins to fail, the natural temptation is to ask what replaces it. Not in the broad triumphant sense of one theory overthrowing another and claiming the whole territory, but in the more practical sense of what kind of language can still be trusted when electric intensity becomes so great that particles, fields, and even empty space stop behaving like the quiet furniture of ordinary physics. The answer is not a single idea. It is a shift in how reality is described. Instead of treating particles as little solid objects with properties attached to them, and fields as smooth influences spreading through a passive background, modern physics treats the world more fundamentally in terms of fields first. Particles appear as excitations of those fields, localized events in something more continuous and more basic. And the vacuum, which in classical thinking was simply the absence of stuff, becomes a physical state with structure, response, and limits of its own. That change sounds abstract at first, but it matters because the strongest electric phenomena cannot be understood honestly without it. In the ordinary world, it is easy to imagine electric force as something one object does to another. A charge creates a field, another charge feels a pull or a push, and the story seems complete. At moderate scales, that picture works well enough. But when the field becomes intense enough, what matters is not only what one charge does to another. What matters is what the field does to the vacuum itself. And the vacuum, in quantum field theory, is not a blank page. It is the lowest energy state of a whole collection of fields that never become entirely silent. Even when no real particles are present, the possibility of fluctuations, virtual processes, and temporary rearrangements remains built into the theory. This is one of the deepest ways in which the modern view differs from classical intuition. Classical emptiness is empty. Quantum emptiness is active. Not active in the sense of fireworks constantly exploding in a theatrical void, but active in the sense that the vacuum has measurable consequences. It can be polarized. It can shift the effective strength of interactions. It can modify energy levels. It can contribute to forces between objects that classical theory would say should feel nothing at all from empty space. So when we begin talking about electric fields of truly extreme intensity, we're no longer discussing a force applied against inert nothingness. We're discussing a force applied to a medium that can answer back. One of the first signs of this appears in vacuum polarization. A charged particle does not sit in empty space as though the vacuum were a perfect blank. The presence of the charge influences the surrounding field structure in such a way that the vacuum behaves a little like a material being polarized. Opposite effective charges are drawn closer, like charges are pushed slightly farther, and the net result is that the bare charge is not experienced in exactly the same way at all distances. The vacuum modifies the effective electromagnetic interaction. In ordinary conditions, this does not create chaos. It creates precise and measurable corrections, the sort of thing quantum electrodynamics handles with extraordinary success. But the deeper meaning is important. Empty space is not passive. It participates in screening and in the scale dependence of charge. That scale dependence becomes especially relevant as one moves towards stronger and stronger fields. What feels like a fixed interaction strength in an introductory setting turns out, under close inspection, to vary with the energy or distance scale at which it is probed. The closer one looks, the more the charge is revealed with less vacuum screening in the way. This does not mean the electron's charge is literally changing as though it were indecisive. It means the effective interaction depends on the response of the surrounding quantum vacuum. Once again, the field is not operating in solitude. It is operating in a world where the vacuum has structure. Now, most of the time, this quantum participation remains subtle. It shifts numbers in a calculation. It alters spectral lines slightly. It contributes to scattering probabilities. It helps explain tiny corrections that experiments can nevertheless measure with astonishing precision. But if the electric field grows strong enough, the vacuum's response stops being a quiet correction and becomes a major event. A sufficiently intense electric field can do something that sounds almost absurd when first stated in ordinary language. It can create matter. More precisely, it can supply the conditions under which particle and antiparticle pairs become real, rather than remaining only virtual features of quantum fluctuation. This is not magic, and it is not matter from nothing in the careless popular sense. The field provides energy. That energy can be converted into a real electron and a real positron, provided the conditions are severe enough. One may picture the vacuum as full of dormant possibility, though that phrase should be used carefully because it can sound too literary. The important point is that quantum field theory allows strong fields to change what counts as physically present. A field that becomes intense enough does not merely pull harder on whatever particles are already there. It changes the inventory of the world. It turns potentiality into actual particles. That process is one of the clearest limits on electric strength as a simple, isolated concept. If you try to create an electric field of enormous intensity in a region of space, there comes a point where the field begins to discharge itself by producing charged pairs. The newly created particles respond to the field, screen it, and carry away energy. The field can no longer be treated as a static external condition that just keeps increasing forever without consequence. Nature introduces a self-regulating mechanism. The stronger the field, the more strongly it invites its own reduction through pair production. In that sense, the vacuum develops tension. It resists being polarized beyond a certain point without changing phase, so to speak, though one should not push the analogy too hard. That phrase, vacuum tension, is helpful if used carefully. It does not mean the vacuum is a rubber sheet in the ordinary mechanical sense. It means there is a threshold beyond which stressing the electromagnetic field configuration ceases to be a harmless deformation of emptiness. Instead, the vacuum responds by reorganizing itself. Once the field is intense enough, what looked like empty space under strain becomes a source of particles that relieve that strain. The quantum vacuum is not infinitely accommodating. It has limits to how far it can be pushed while remaining the quiet lower state we were pretending it to be. This is a profound idea because it changes the meaning of strength. In classical language, a stronger field is simply more of the same. In quantum field language, a stronger field can become a qualitatively different object. It may stop being a background and start being a dynamical participant in creating, accelerating, and interacting with matter. Strength stops being just a number and becomes a regime. That is why the strongest electric force is not merely a classical extreme, it is a threshold story. As strength grows, new behavior comes online. There is another subtlety here as well. The vacuum does not merely produce pairs and then go back to sleep as though nothing happened. The created particles alter the field, absorb energy, and contribute to what is called back reaction. This means one cannot always separate the field from the matter it generates. The system becomes coupled to itself in a deeper way. You begin with a strong electric field, but the field changes the vacuum produces particles, the particles affect the field, and the whole configuration evolves together. That kind of feedback is one more reason why simple notions of unlimited electric strength break down. Nature does not allow fields to be strong in isolation forever. Strong fields generate circumstances that change the field. It is worth pausing on how dramatic that is. The everyday intuition about force is that it acts on existing things. Push a box, pull a rope, attract a particle, repel a charge. But at the quantum field level, very strong electric fields do not merely act on existing matter. They help determine whether matter is there at all. They move from being influences to being part of the process by which physical content appears. That is an extraordinary broadening of what force means. It is no longer just interaction among objects. It becomes part of the boundary between vacuum and particle reality. All of this still takes place within quantum electrodynamics, which is among the best tested and most accurate theories ever constructed. That is worth emphasizing because it prevents the discussion from floating away into vague speculation. These are not dreamy philosophical claims about emptiness having feelings. They are precise consequences of a theory whose predictions have been confirmed to astonishing accuracy. Yet the very success of quantum electrodynamics also sharpens the question of ultimate limits. The theory is powerful, but like all our current frameworks, it is expected to be incomplete at sufficiently high energies and sufficiently short distances. It describes electromagnetic interaction beautifully within its domain. It does not pretend to be the final unified account of everything. That incompleteness becomes visible in several ways One is practical. As the energy scale rises, the effective electromagnetic coupling changes. Another is conceptual. Quantum electrodynamics treats space-time as a classical background. It quantizes the electromagnetic field and matter fields, but not the geometry of space-time itself. That is fine for most accessible phenomena. But once field energies and distances approach the most extreme natural scales, one can no longer safely assume that gravity and space-time geometry remain classical spectators. A strong electric field carries energy density. Energy density gravitates. Enough of it, concentrated tightly enough, should influence space-time in a serious way. This means that the limits of electric strength are not purely electromagnetic. They are already beginning to bend toward gravity. If one imagines an electric field becoming more and more intense in a smaller and smaller region, eventually the energy stored in that field becomes so large that gravitational effects can no longer be ignored. The field is not just living in space-time, it is helping curve it. At that point, the distinction between electric intensity and gravitational structure begins to fade. One cannot ask how strong the electric field is without also asking what the field is doing to the geometry in which it exists. That realization is one of the reasons Planck's scale language becomes unavoidable. The Planck regime is not special, because physicists enjoy giving severe names to severe ideas. It is special because it marks the point where the constants associated with quantum mechanics, relativity and gravity, combine to define scales beyond which our current separate theories are expected to fail as independent descriptions. So if a field becomes strong enough that its energy density pushes toward that domain, the correct description must involve more than quantum electrodynamics in flat or gently curved space-time. It must involve whatever deeper theory eventually unifies quantum field structure with quantum geometry. Before getting all the way there, though, there is still more to say about the vacuum itself. The quantum vacuum is not only a place where pair production happens under extreme fields, it is also the arena in which nonlinear electromagnetic effects can appear. Classical electromagnetism is linear in a certain important sense. Fields can superpose cleanly. The vacuum does not usually make one electromagnetic field directly scatter from another in an obvious way. But quantum corrections allow richer behavior. In sufficiently intense regimes, light can indirectly interact with light through virtual charged particles. The vacuum behaves less like an inert, transparent nothing, and more like a medium with subtle nonlinear properties. Again, the effect is tiny under ordinary circumstances, but conceptually it is enormous. It means even radiation moving through vacuum is not entirely independent of the quantum structure of that vacuum. This deepens the idea of vacuum tension. The vacuum is not merely the absence of particles, it has response functions, effective properties, and thresholds. It can be polarized, stressed, and driven into new behavior. A strong electric field is therefore not pushing against emptiness in the classical sense. It is pushing against a quantum medium whose silence is conditional. This makes the very phrase strongest electric force more complicated in an interesting way. Strength is limited not only by external conditions or by the fragility of matter, but by the willingness of the vacuum to remain vacuum under stress. There is also a quiet lesson here about how physical law enforces humility. If one were inventing the universe with only classical instinct, one might assume that stronger electric fields are simply attainable by taking more charge and less distance without changing anything else. Quantum field theory refuses that simplification. Stronger fields change the vacuum. Stronger concentrations demand back reaction. Stronger energies threaten to involve gravity. Every step upward in intensity recruits more of reality into the answer. It is as though nature insists that no fundamental question be allowed to remain provincial for long. This is why the quantum field view is so important for our story. It shows that the limit of electric strength is not just a matter of bigger numbers, it is a matter of qualitative transitions. One threshold brings pair creation, another brings serious vacuum polarization and nonlinear behavior. Beyond that lies the regime where space-time itself must answer, And throughout all of this, the classical notion of force as a clean relation between two static charges becomes less and less central. What matters instead are fields, energy density, particle creation, effective couplings, and the dynamical structure of the vacuum. There is something almost architectural about it. The ordinary electric force is like the visible part of a building, the doors, walls, and windows you interact with every day. Quantum field theory shows you the wiring inside the walls. Vacuum response shows you that the walls themselves are under tension. Strong field effects show you that the wiring can alter the structure of the house if overloaded. And as you keep pushing, gravity appears and reminds you that the ground beneath the building is not fixed either. At some point, you're no longer asking whether the lamp is too bright. You're asking how much strain the whole structure of reality can absorb before it changes category. This does not mean the electric force becomes less real or less fundamental as we move into these deeper descriptions. If anything, it becomes more interesting. The simple pull and push between charges turns out to be only the surface expression of something richer, mediated by fields, conditioned by quantum vacuum structure, and bounded by the onset of new physics when intensity grows too great. The force is still there, but its deepest meaning lies in the framework that contains it, not in the simplified classroom image that first introduces it. It is also worth keeping in mind that the vacuum limits on electric strength are not signs of weakness in the universe. They are signs of richness. A poorer theory would let fields grow without consequence until one simply declared an arbitrary cutoff out of embarrassment. Quantum field theory does something better. It predicts how strong fields begin to create new phenomena. It tells us the vacuum is not infinitely compliant. It gives physical reasons why unlimited extrapolation fails. That is not a retreat from explanation. It is a more mature form of it. And yet, even this maturity has a horizon. Quantum electrodynamics and strong field vacuum effects tell us a great deal about how electric strength behaves before the deepest scale is reached. But once the field energy and concentration become large enough that space-time geometry must be treated quantum mechanically, this framework too becomes incomplete. That is where the road bends again. The vacuum has shown its tension. The field has shown its power to create particles. The limits of strength have revealed themselves as thresholds rather than simple ceilings. But beyond those thresholds lies an even sterner region, one where gravity is no longer the slow, distant force of planets and stars, but a local participant in the fate of extreme fields. And that is exactly where the next part of the story has been waiting all along. Because if electric intensity can pull the vacuum into action, and if enough concentrated field energy can begin to matter gravitationally, then the boundary between electromagnetism and gravitation starts to look much thinner than it first seemed. At that point, one is no longer only asking how strong an electric force can become. One is asking what happens when charge, space-time, and the deepest natural scales meet in the same place, and why black holes, Planck regimes, and the edge of physical law keep appearing whenever we try to follow that question to the end. By the time black holes enter the discussion, the question has changed its posture again. It is no longer standing in the familiar room of atoms, sparks, or even strong fields acting in an otherwise empty region of space. It has moved into a much harsher setting, one where energy, charge, geometry, and the structure of the vacuum all begin pressing against one another at once. And this is why black holes matter so much to the story of electric force. They are not interesting merely because they are dramatic, though they certainly have never had a problem attracting attention. They matter because they force physics to confront a difficult truth. A field can become so intense, and energy can become so concentrated, that space-time itself must be treated as part of the system rather than as a quiet stage on which the system unfolds. Once that happens, ordinary questions about how strong an electric force can get become inseparable from questions about gravity, horizons, singularity, and the deepest scales nature seems to possess. Up to now, we have followed electric strength through several levels of seriousness. We began with the ordinary electromagnetic world of matter, chemistry and structure. Then we moved into extreme attraction, where quantum rules had to prevent collapse, then into strong fields, where the vacuum refused to remain passive and began creating particles of its own. At each step, the lesson was the same. Electric force does not grow in isolation. The stronger it becomes, the more of reality gets recruited into the response. Black holes are what happens when that recruitment includes space-time geometry in the most uncompromising way. Their gravity no longer acting as a distant organizer of stars and planets, but as a local and decisive transformation of the structure of space and time. The simplest mental picture of a black hole is often too simple. One imagines a kind of cosmic drain, a hole in space into which matter falls never to return. That image is not entirely wrong, but it misses the most useful idea. A black hole is better understood as a region where mass and energy have curved space-time so strongly that there exists a boundary, the event horizon, beyond which escape to the outside universe is no longer possible. This is not a material surface in the ordinary sense. It is a geometric condition. And that already makes black holes relevant to our question, because electric fields carry energy, and energy contributes to gravitation. So if you concentrate enough electromagnetic energy into a small enough region, you are not merely making the electric interaction stronger. You are helping to shape the geometry in which the interaction exists. This is one of the reasons the phrase strongest electric force becomes increasingly inadequate near the deepest frontier. In the everyday world, force is something one object exerts on another. Near black holes and Planck scales, the electric field is no longer just an influence among charges. It becomes part of the energy content that helps determine the curvature of space-time. The field is in the architecture now. You cannot ask how strong it is without asking what the geometry is doing in response. That is a major shift in perspective, and it is one of the places where the familiar classical idea of separate forces living inside a fixed arena stops being trustworthy. Charged black holes make this especially vivid. In general relativity, it is possible to describe a black hole that carries electric charge. Such an object differs from an uncharged black hole because the electric field outside it contributes to the total structure of the space-time. Gravity pulls inward, electric effects contribute their own structure, and the result is a black hole with a geometry that depends not only on mass but also on charge. This already tells us something important. Charge is not an optional decoration on top of gravity. In the right setting, it changes the very shape of the solution. But charged black holes also come with an especially instructive constraint. There is a limit to how much charge a black hole can have relative to its mass, while still remaining a black hole in the usual sense. If the charge becomes too large compared with the mass, the horizon structure changes in a way that suggests something has gone wrong. In simple terms, gravity may no longer be able to conceal the central pathology behind an event horizon. One approaches a case called extremality, where charge and mass are balanced in a very particular way, and beyond that, the ordinary black hole solution threatens to lose its defining protective boundary. That balance is not a small detail. It is one of the sharpest signs that electric strength and gravitational structure are intertwined at a deep level. A charged black hole cannot simply accumulate charge indefinitely as though gravity were an inattentive accountant. There is a relationship between how much mass the object has and how much charge it can sustain before the geometry stops behaving in the familiar black hole way. Nature appears to prefer that singular behaviours remain hidden behind horizons. Physicists refer to this general hope through ideas related to cosmic censorship. The notion that the worst pathologies of space-time should not be laid bare for distant observers. Whether that principle is universally true in every conceivable circumstance remains a subtle question, but the charged black hole certainly hints that there are strong limits on how far one may push charge relative to gravitational confinement. Now, one might be tempted to interpret that as the answer to the whole story. Perhaps one could say, The strongest electric force nature allows is whatever a black hole can support before crossing into that extremal condition, but that would still be too simple for several reasons. First, a larger black hole can carry more total charge than a smaller one, so there is no single universal charge ceiling in that sense. Second, total charge is not the same thing as local field intensity. Third, a real charged black hole would not exist in splendid isolation from quantum effects. Strong electric fields near the horizon can trigger pair creation, and that pair creation can discharge the hole over time. In other words, the black hole does not get to keep all the charge. It might classically be assigned without the quantum vacuum interfering. This is one of the most elegant parts of the story. Classical gravity allows charged black hole solutions. Quantum field theory then arrives and says very well, but if the electric field near the horizon becomes too intense, the vacuum will answer. Particle pairs can be created. One sign of charge can fall in, the other can escape, and the black hole begins to lose its net charge. So even here, at the edge of general relativity, the earlier lesson returns. Extreme electric strength invites new behaviour that tends to limit its clean persistence. The vacuum is still not passive. It remains one of nature's preferred ways of refusing unlimited extrapolation. There is something almost pleasingly stubborn about that. Again and again, whenever we try to imagine electric intensity growing without consequence, another layer of physics arrives to object. At atomic scales, quantum structure prevents collapse. In strong external fields, pair creation intervenes. Near black holes, space-time geometry and horizon structure impose further discipline, and quantum effect can actively discharge the system. The universe does not permit simple one-parameter escalation for very long. It insists on adding complications, which is often just another word for deeper truth. This is exactly why Planck scales matter so much. The Planck scale is not just one number or one threshold. It is a family of natural scales built from the deepest constants of the theories we already have. Planck length, Planck time, Planck mass, Planck energy, Planck charge. These are all attempts to identify the region where the separate frameworks of quantum theory and general relativity are expected to stop functioning independently and begin demanding a more unified description. When physicists speak about the edge of physical law, they often mean this region. Not the edge in the sense that nature ends there, as though one could step off into blankness. Rather, the edge in the sense that our present conceptual tools begin to overlap, interfere, and lose their clean separation. To understand why this matters for electric force, imagine trying to localize charge into a region approaching the Planck length, while allowing the associated energy density to become immense. The electric field becomes enormous, but so does the energy concentration. That concentration should gravitate, the geometry should respond, yet at the same time the region is so small that quantum uncertainty becomes severe, and the very idea of smooth space-time at that scale becomes doubtful. So, what are we even describing now? Is it an electric field in space? Is it a quantum excitation in a fluctuating geometry? Is it the seed of a microscopic black hole? Is it something for which our present categories are simply too blunt? This is why the Planck regime is the edge of physical law. It is where our most successful languages all start speaking at once, but not yet in perfect agreement. Black holes hover at this boundary in a particularly revealing way, because they bring gravity to the forefront without allowing us to forget the rest. A very small black hole, especially one near Planck mass, would be an object for which quantum gravity effects could no longer be ignored. It would not be correctly described by classical general relativity alone, nor by quantum field theory on a fixed background alone. If such an object also carried charge, the electromagnetic aspect would have to be part of whatever deeper description replaced our current patchwork. The electric field near it would not simply be an addition to the story. It would be one of the things that help define the story. And this is where the tone of physics changes a little. For much of the electromagnetic world, we enjoy theories of astonishing predictive power. In quantum electrodynamics, we can calculate effects with absurd precision. In general relativity, we can predict the motion of bodies and the structure of black holes with breathtaking success in the appropriate domain. But at the Planck edge, certainty softens. We no longer have a single complete experimentally confirmed theory that unifies gravity and quantum field structure in all their depth. We have candidates, approaches, insights, partial structures, clever mathematics, and serious hopes, but not final possession. That is why this region is so fascinating. It is one of the few places in modern physics where the map is detailed enough to know that there is unknown territory ahead. This uncertainty should not be mistaken for ignorance in the simple sense. We know a great deal about why the edge exists. We know why combining very high energy, very short distance, strong curvature, and quantum behaviour pushes our current theories into tension. We know why Planck units arise. We know why black holes become relevant to concentrated energy, and why charge changes their structure. What we do not yet know completely is the final language in which all of those truths are to be written together. That is a subtle but crucial distinction. The frontier is not empty. It is crowded with partial understanding. There is also a more philosophical aspect to black holes in this story, though it is best approached carefully and without too much theatrical fog. Black holes force us to confront the fact that information, geometry, field theory, and quantum behaviour are more deeply linked than the older picture of separate forces would have suggested. The black hole information problem, horizon thermodynamics, Hawking radiation, and related ideas all hint that space-time itself may have a more microscopic structure than classical geometry reveals. If that is true, then asking about maximum electric force is not just asking how hard charges can pull or push. It is asking how interaction, geometry, and information are organised at the most basic level. That is a much bigger question than it first appears. Even the notion of singularity plays an interesting role here. In classical general relativity, certain black hole solutions contain singularities, places where curvature becomes unbounded and the theory ceases to give sensible physical predictions in its usual form. Most physicists take this not as evidence that singularities are ordinary physical objects we should accept with cheerful literalism, but as signs that the classical theory has been pushed beyond its domain. In that sense, singularities are like the infinities that appeared earlier in classical electrodynamics around point charges. They are signals of breakdown. They say this description has run out of road. At the centre of the black hole story, then, is the same lesson we have seen before, only with higher stakes. When physical quantities become too extreme, the theory that produced them begins to confess its own incompleteness. That confession is precisely what makes the Planck scale meaningful. It is the scale suggested by the constants, where such breakdown should no longer be postponed. Not every black hole is a Planck scale object. Not every strong electric field approaches quantum gravity. But the line connecting them is real. The more intensely you compress energy and charge, the more gravity and quantum structure insist on joining the same description. Black holes are one end of that bridge. Planck scales are the signpost telling you where the bridge reaches beyond the theories we currently trust in isolation. There is something quietly satisfying about how this reframes the question of electric strength. We began by asking how strong electric force can get, a question that sounds at first like it belongs entirely to electromagnetism. But by following it honestly, we have been led through atomic structure, vacuum instability, quantum field corrections, and finally into the geometry of black holes in the Planck frontier. The force did not stop being electric. Rather, the universe revealed that electric strength at its deepest limit is never only electric, it drags the rest of the foundations into view. One can see this even in the simplest comparison between gravity and electromagnetism at the natural scale. In everyday life, gravity feels dominant because planets, stars, and your own posture keep reminding you that downward is not a suggestion. At the level of particles, electric interaction is vastly stronger. But at the Planck scale, the natural strengths implied by the constants become comparable in the sense that our usual separation of roles begins to dissolve. Charge, energy, distance, and curvature all live on the same severe stage. That is one of the great conceptual unifications hidden inside the Planck idea. It shows that the neat division of labour we enjoy at accessible scales may be a temporary convenience rather than a final truth. Black holes also bring time into the story in a subtler way. Near an event horizon, the structure of time itself as experienced by distant and local observers becomes strange. Clocks behave differently. Causal order becomes constrained by the geometry. If one is trying to imagine electric processes near such conditions, one must remember that even the pacing of events is no longer something one may treat as universal and simple. This matters because force, field evolution, particle creation, and discharge all unfold in time, and time near strong gravity is not the easy common background of ordinary intuition. Once again, the edge of physical law is not merely about large values. It is about the deformation of the very concepts by which we normally organise values, and yet, for all this severity, black holes are not only destroyers of clarity, they are also teachers. By testing our theories against them, physicists have learned an enormous amount about what must be true in any deeper framework. A successful theory of quantum gravity must account for horizon thermodynamics. It must explain how geometry and quantum information relate. It must reduce to general relativity where general relativity works, and to quantum field theory where quantum field theory works. It must handle charge, mass, and radiation in consistent ways. In that sense, black holes are not merely the edge of law. They are one of the sharpest tools we have for discovering what a deeper law must look like. This makes them a fitting companion to the Planck scale. The Planck units tell us where our current theories should begin to fail together. Black holes show us concrete situations in which those failures become urgent. Charge adds another layer by introducing electromagnetic structure, vacuum discharge, and extremal conditions. Together they create a kind of stress test for the foundations of physics. And stress tests are invaluable because they reveal not only what survives but what assumptions were doing hidden work all along. So when we stand at this edge, looking at black holes, Planck scales, and extreme electric intensity all at once, the picture is not one of chaos, it is one of convergence. Different parts of physics that usually mind their own business begin to overlap. Classical geometry overlaps with quantum fluctuation. Electromagnetic fields overlap with gravitational curvature. Vacuum structure overlaps with horizon physics. The question of strongest electric force becomes a question about how these overlapping descriptions can be made into one coherent account. That coherent account is not yet finished, but the path to it has become surprisingly visible. It runs through the fact that charge has a natural scale. It runs through the fact that intense fields can create particles. It runs through the fact that energy gravitates. It runs through the fact that black holes cannot sustain arbitrary charge without structural consequences. And it runs through the Planck frontier, where our current theories become too successful in their own domains to remain comfortably separate. If there is an edge of physical law, it is not a cliff, but a crowded shoreline where several great theories wash up against one another. And that is why the story cannot end by simply admiring the horizon from a distance. Once black holes and Planck scales have entered the discussion, the final question becomes unavoidable. Not merely how strong electric force can get in some dramatic abstract sense, but what the best honest answer actually is once all these layers are included. After tracing charge from atoms to vacuum breakdown to the edge of space-time itself, we are finally ready to face the central question directly and ask, with all due care and without pretending the answer is simpler than it is, how strong electric force really can be. So after all that, after the balloon on the wall and the atom that refuses to collapse, after Coulomb and quantum fields and the vacuum quietly objecting when pushed too hard, after the fine structure constant and the Planck charge and the charged black hole standing at the edge of space-time like a very severe exam question, we can finally return to the thing we have been circling from the beginning and ask it plainly. How strong can electric force really get? The most honest answer is that there is not a single simple maximum in the everyday sense. Nature does not place one neat number on a shelf and label it strongest electric force. Do not exceed. What nature gives us instead is a hierarchy of answers, and each one becomes more serious as the conditions become more extreme. If you mean electric force in the classical classroom sense, between charges that can be brought closer and closer together, then the force can keep increasing as distance shrinks. In that idealized picture, there is no natural stopping point built into the equation itself. But that answer is only true inside a world that is pretending not to notice what happens when distance becomes very small, when energy becomes very concentrated, when the vacuum is no longer quiet, and when space-time itself begins to care. In other words, the classical answer is not false, but it is incomplete in exactly the way that matters most here. A better answer begins by saying that electric force can become enormous long before it reaches anything like its deepest conceivable limit. It is already overwhelming at the scale of particles. It already shapes atoms, chemistry, matter, biological life, and the entire practical electrical world we have built around ourselves. Compared with gravity between elementary particles, it is staggeringly strong, so there is a sense in which electric force begins this story, in a position of almost unreasonable importance. It does not need to be pushed to some cosmic boundary before it becomes fundamental. It was fundamental from the start. The real question is not when electric force becomes important, but when its familiar description stops being enough. That is where the answers begin to split into layers. At one level, electric force becomes too strong in the practical sense when it starts tearing matter apart, stripping electrons from atoms, driving plasmas, or producing violent discharges. A lightning bolt is already far beyond what human intuition can comfortably file under ordinary interaction. Yet lightning, for all its drama, is still not the deepest expression of electric strength. It is an atmospheric event, not a boundary of physical law. It is intense, but it takes place inside a world where atoms, air, and classical fields are still mostly meaningful ideas. Push farther, and the next answer appears. Electric force becomes too strong for the vacuum to ignore. Once an electric field is intense enough, empty space in the classical sense ceases to be empty in the useful quantum sense. Particle pairs can be created. The field begins to turn energy into matter and antimatter. It does not simply pull harder on what is already present. It changes what is present. That is a profound shift, because it tells us that electric strength is no longer just a matter of force between existing charges. It has become a matter of whether the vacuum itself can remain vacuum under the strain. This gives us a more realistic kind of limit, not an absolute final maximum, but a threshold where electric intensity stops being something that can be increased cleanly without consequence. Beyond that point, nature begins to regulate the situation through pair creation, screening, and back reaction. The stronger the field, the more vigorously the vacuum answers back. In that sense, truly extreme electric fields are self-resisting. They invite the processes that reduce or reshape them. So one important answer to our question is that electric force can become strong enough to destabilize the vacuum well before it reaches the deepest natural benchmark. Nature starts objecting early, and yet that is still not the last answer, because vacuum instability is not the end of the story. One may still ask what the most fundamental scale of electric interaction would be if charge and distance were both pushed all the way to their natural limits. This is where the Planck charge matters, and where the whole discussion becomes both sharper and more delicate. If you take the natural scale of charge suggested by the constants of physics, and then imagine that charge acting across the natural shortest scale, where our ordinary ideas of space are expected to remain trustworthy, the resulting force sits at the natural force scale associated with the Planck regime. In plainer language, the strongest electric force we know how to define in the deepest natural sense is of Planck order. That sounds like a clean answer, and in one sense it is. If you want the most severe natural benchmark, that is the one. But it comes with an important warning attached. The moment you say Planck order, you are no longer safely inside ordinary physics. You are at the frontier where quantum mechanics, electromagnetism, gravity, and possibly the microscopic structure of space-time all demand to be included at once. So the strongest electric force we can define naturally is also the force scale at which the very idea of force, at least in the simple classical sense, starts losing its independence. We can point to the scale. We cannot yet claim to possess the final complete theory of what happens there. This is why the strongest electric force is not best imagined as a giant invisible tug between two ordinary charges. At the deepest level, it is better understood as the scale at which concentrated electric interaction becomes inseparable from the rest of fundamental physics. A sufficiently extreme electric field carries enormous energy density. That energy density gravitates. Strong enough concentration should affect space-time itself. At that point, asking how hard one charge pulls on another is no longer the whole question. One must also ask what happens to the geometry around them, whether the vacuum remains stable, whether particle creation discharges the field, and whether the region being described is already pressing into a regime where a quantum theory of gravity is needed. That is the real shape of the answer. Electric force can become astonishingly large, but not in a way that leaves the rest of reality unchanged. Every time you try to make it stronger, more of the universe enters the discussion. At first, matter enters. Atoms rearrange, electrons are stripped away, chemical structures collapse. Push harder, and the vacuum enters. Particle pairs are produced. Push harder still, and gravity enters. The energy of the field begins to matter geometrically. Push farther, conceptually at least, and you meet the Planck frontier, where the separate languages we have relied on stop agreeing on who gets to speak first. This layered answer is more satisfying than a single maximum, because it matches what physics has been teaching us all along. Nature does not tend to enforce its limits with a single crude wall. It enforces them by changing the rules of the game as you approach the wall. A classical law works beautifully until quantum structure becomes relevant. A quantum field description works beautifully until gravity can no longer be neglected. A gravitational description works beautifully until the full quantum nature of geometry becomes unavoidable. Limits are rarely just the largest value of a quantity. More often, they are the places where one kind of understanding must yield to a deeper one. There is a lovely symmetry in that. Electric force begins life, in our minds at least, as something almost embarrassingly simple. Things attract or repel. Hair stands up, sparks jump, balloons misbehave. But if you follow the question of strength honestly, it leads you all the way to the edge of what modern physics knows how to describe. It becomes a question not only about electricity, but about natural units, quantum fields, vacuum structure, black holes, and the fact that space-time itself may not be the smooth passive stage we once imagined it to be. A child could ask the first version of the question. A quantum gravity research group could spend years trying to answer the last version. That is usually a sign that a question was worth asking. Another part of the answer is that total charge and local force are not the same thing. A large object can carry an enormous net charge and still not produce the most extreme possible local electric interaction if that charge is spread out over a wide region. By contrast, a much smaller amount of charge packed into a tiny region can create a much more severe field. So if one says strongest electric force, one must be clear about what is being measured. The largest total charge nature permits in some object is one question. The largest stable electric field is another. The strongest local interaction across the smallest meaningful distance is another still. That is why black holes are so instructive. They show that charge alone is never enough. Mass matters, size matters, geometry matters. charged black holes also underline another subtle point. Even when classical general relativity allows a highly charged black hole solution, quantum effects are likely to prevent that charge from remaining indefinitely untouched. The black hole can discharge through pair creation. The horizon and the field together create conditions under which the vacuum once again intervenes. So even in one of the most extreme settings known to theory, electric strength is not allowed to sit there in splendid isolation like a king on a throne. It is always embedded in processes that limit, transform, or drain it. That seems to be one of the deepest themes in the whole story. Electric force can become extraordinary, but extraordinary force invites extraordinary response. The vacuum responds, matter responds, space-time responds. Our theories respond by revealing their own edges. There is no simple path from familiar electric interaction to unlimited intensity. Every step upward recruits new physics. This is also where the fine structure constant quietly returns as part of the answer. The reason our ordinary world is not consumed by electromagnetic severity is that the charge carried by familiar particles, especially the electron, is not at the maximal natural scale. It is smaller in just such a way that atoms are stable, chemistry is rich, and quantum electrodynamics behaves remarkably well. The Planck charge gives us the natural reference scale, and the fine structure constant tells us that the ordinary electromagnetic interaction is strong enough to matter deeply, but not so strong that everything immediately collapses into a much harsher regime. In that sense, the everyday world lives in a kind of electromagnetic middle ground. Not weak, certainly not weak, but restrained. That restraint is one of the reasons the question is so compelling. The universe could, in principle, have been set up very differently. Electromagnetic interaction could have been far more severe at ordinary scales. If so, atoms, molecules, and chemistry would look radically different. Instead, the world we know exists in a region where electric force is powerful enough to build structure but not so overbearing that stable complexity becomes impossible. That does not explain why the constants have the values they do, but it sharpens our sense of what those values accomplish. So how strong can electric force really get? The best honest answer is something like this. In a simple classical idealization, it can grow without built-in bound as charges are increased and distance is reduced. In the real quantum world, very strong fields reach thresholds where the vacuum becomes unstable and begins producing particles, so the force can no longer be treated as a clean isolated background. At the deepest natural scale, if charge and distance are pushed to the limits suggested by Planck units, electric force reaches a Planck scale intensity, where electromagnetism, quantum theory and gravity all become inseparable. That is the strongest natural force scale we know how to define, but it lies precisely at the edge where our current theories stop being complete on their own. In other words, electric force can get stronger than any ordinary process we know, stronger than matter can comfortably survive, stronger than empty space can quietly tolerate, and finally as strong as the very foundations of physical law can meaningfully describe before those foundations have to be unified more deeply. That is not a single maximum in the household sense. It is a cascade of thresholds ending at a conceptual horizon. There is something satisfying in leaving the answer there, not because it is vague, but because it is honest. Physics has given us a way to trace the question all the way from static, cling to the Planck frontier without pretending that the final terrain is already settled in every detail. We know enough to say that unlimited extrapolation fails. We know enough to say that the deepest natural scale of electric strength is of Planck order. We know enough to say that before that scale is even reached, quantum field effects and gravitational considerations begin crowding the problem. And we know enough to see that the question was never only about electricity. It was a way of asking how the universe handles extremes. That may be the nicest thing about the whole journey. The question began sounding almost practical. How strong can electric force get? It could have been a line from a textbook, a challenge from a curious teenager, or the sort of thing one wonders after being mildly insulted by a doorknob in winter. But it turned out to be one of those questions that widens as you approach it. It asked about force and ended up asking about matter, vacuum, geometry and the edge of law. It asked about charge and ended up revealing the structure of the physical world more broadly. Good questions do that. They begin locally and end cosmically. And now here you are, a little farther along this strange road than when we began. Perhaps it is later where you are now. Perhaps the room is quieter. Perhaps the mind, after spending all this time with atoms and fields and horizons, is beginning to loosen its grip a little. If so, that seems fitting. Electric force, for all its invisible rigour, has carried us a very long way. From the smallest architecture of matter to the most severe scales nature seems to allow, it has shown itself to be not only one of the fundamental interactions, but also one of the best guides to where our understanding becomes deepest and most incomplete at once. So if you find yourself thinking back on the question tomorrow or next week or the next time a spark jumps unexpectedly from your hand to some innocent metal object, it may be worth remembering that behind that tiny event lies a force powerful enough to shape matter, disturb the vacuum, challenge space-time, and carry physics to the threshold of its own unfinished future. And that really is the final answer in the only sense that matters. Electric force can get strong enough to stop being just a force and become a doorway into the deepest questions we know how to ask.